Let's see. Red. So I think we're good. We're good. All right, guys. So it's 7, and we're going to get started. And I talked to a few of the students this morning, and I asked them what they thought their opinion would be on how we should do the order, of the review tonight. And a good amount of them were like, can we please do spectroscopy first? And instead of doing nomenclature first, because there's no new information for nomenclature. So I'm still going to do nomenclature. I'm going to do the entire thing, no matter what. I'm going to do the entire thing, but I'm going to switch up the order, okay? So instead of working the exam from front to end, right, nomenclature all the way down through synthesis, through to spectroscopy, I'm going to do it opposite, okay? So we're going to change it up, and we're going to start with spectroscopy instead, okay? Just so that we can... I think that's really important since it's the new section for this exam, right? Before we get started, does anyone have any general questions about anything? No? Okay. And in addition to that, so Chance couldn't make it tonight, but we do have our amazing tutors. Well, right now it's just Danny. So our amazing tutor, Danny, right? And then we'll have Andres coming, and then maybe a couple others, right? So if you have a question at any point, please raise your hand and make them work, make them come to you and answer your questions, okay? And if they can't answer it, then raise your hand again and get another tutor, okay? And if they can't answer it, then ask me. And if I can't answer it, then we need to be better tutors, right? So let's get started, okay? With spectroscopy. So first of all, the last section of the exam, spectroscopy, what she's going to give you is a molecule, right? She's going to give you the molecular formula. So how many atoms, how many carbons, hydrogen, so on, right? And then she's also going to give you the an IR spectrum. She's going to give you a proton NMR spectrum. And then she'll give you probably a C13 NMR, okay? So she's going to give you those 3. You probably will not need the C13 at all. You can solve all of these without it, right? But if you want to, you can look to that as well, okay? So here you can see the compound. I'm going to highlight what it is. Okay? And what the first spectrum that's given to us is called the IR, okay? This right here. Okay? And that stands for infrared radiation spectroscopy. And what I'm going to do, I added a page here just so that we can talk a little bit what it's about, right? I don't want to go too much into the theory about it, but what is important about it, okay? Okay, so as I said, this is going to stand for infrared. Okay, so what you have your sample of that molecule, right, in the question, and you're going to hit that sample with infrared radiation, okay? So let's say it's in our container. You hit it like this with infrared radiation, all right, on our electromagnetic spectrum, okay? And then what that's going to do to the molecules in the sample, right? You need to imagine that you have a spring, okay? So the left ball is going to be, for example, carbon, and the right one is going to be some other atom, okay, like hydrogen, right? When you hit it with the infrared radiation, at a specific frequency, it's going to cause these 2 atoms to oscillate, right? Like a spring. So they're going to oscillate. I don't know how to show that here, but they're moving, right? And that's going to be different depending on the atoms that are bonded to one another, right? So C to H versus C to C, for example, okay? And so that frequency, that specific frequency for that bond is going to differ based upon 2 factors. Does anyone know what they are? The 2 factors? So we're talking about the frequency at which these are going to, what frequency of radiation you have to hit it with for them to oscillate, right? So that's going to differ upon 2 things. So I'll put depends upon. The first thing is going to be the mass of the atoms. Okay? Second thing is going to be the bond strength, right? So that could mean if you have a triple bond, right? A pi bond, a double bond, right? Anything like that. If you have a carbon bonded to oxygen, that would be stronger than carbon bonded to carbon, right? So that's your examples. So all of these are going to have different frequencies, and they're going to show up here in our graph, right? The absorptions. And so you have these two axes, and the one at the bottom is representing wave numbers. On the side, percent transmittance. And your wave numbers, they use the wave numbers because that is directly proportional to the frequency. Okay? Okay, so as we're going to the left across the spectrum, we're going up in frequency. You can think of it that way, okay? So the stronger bonds will be further to the left, right? Things with heavier atoms, right? As long as you're keeping one thing constant, right? If you're keeping the bond strength constant and you're changing the mass, it's going to be further to the left, okay? And so you have to be able to recognize where on the spectrum these absorptions are taking place, right? Percent transmittance. So you can see if you were to put like little lines across here. Can you guys see? Little lines. So as the percent transmittance goes lower, right? That means the percent absorbed is higher. Does that make sense? So now let's look at our absorptions that are present. So I recommend when you're doing these, first thing you want to do is, well, this isn't technically the first thing, but I'm explaining the IR, right, part. So I want you to put a line down the 1,500, okay? And everything to the right of that, everything to the right is called what? What's that region called? Fingerprint, okay? And that's going to be specific to a particular molecule depending upon the single bonds that it has, right? Like if you have a carbon-oxygen bond, that's what that's telling you, and it's very hard to decipher from it. So just cross it out and ignore it, right? Look at everything to the left of the 1,500 mark, okay? So right here, right, we have something at around 1,600. So to the left of that fingerprint region, I'm just going to ballpark it right here, for example. You're going to have your double bond region. So that could be what kind of double bonds? Carbon-carbon, carbon-oxygen. That's where you're going to find them, that double bond region. Right here, you're going to find triple bond region, right? So that could be carbon to carbon, that could be carbon to nitrogen, okay? And then the next place I would want you guys to mark is right down to 3,000, okay? So what's important about this is you're going to start to see the carbon to hydrogen bonds, all right? So on the right of this line, you're going to see sp3 carbons bonded to hydrogen, okay? So of course, with a lot of organic molecules, you're going to see a bunch of those, right? You can't use that to decipher anything, to set it apart. To the left, so that's going to be to the right, so I'll put like an arrow that is to the right. To the left of that line is going to be what hybridization? sp2 hybridized carbon to hydrogen bonds, all right? And even further to the left, sp hybridized carbon to hydrogen bonds, okay? In this region, okay, to the left of the 3,000, he said, so that's going to be your terminal alkynes, like that. So that's sp hybridized, correct? sp hybridized carbon. And then you're also going to see distinctive, it's going to be your OH, as well as what other functional group? Very good. So your OH and your NH are going to be present in these regions, okay? And your OH is going to be this broad dip, okay? Which is exactly what we happen to see in this molecule. All right, so that's the overview. Now that we did that, I'm going to erase, so you can take a picture if you want to. Okay, take a picture if you want to. And then the first step when you're doing this, what do you think that you should do when you're doing these problems? That was just my overview. So even before that, like in the question, what are you given? You're given a molecule, right? So what can you exactly? That's what I was looking for. So I want you guys to calculate the unsaturation number, okay? And what's the formula for that?
Carbon times 2.
2 times the carbon.
Plus 2.
Plus 2. And then subtracted by the number of hydrogens that you have in that particular molecule. Right? And then this is all going to be over 2. Okay, so for Orgo 1, you just want to know that the oxygens, they don't make a difference in terms of the unsaturation number. Okay, for halogens, you would count them as a hydrogen, so you subtract as well. So you could also put minus X if they were to give you a halogen, but really that's not common, and nor do we see it in this question, so I'm not going to put it here, okay? So we're ignoring the oxygens. So everyone, I want you guys to all solve for the unsaturation right now. Make sure we get the same thing. All right. So you got 2 times 9. Okay, did you guys get 4? Good. Okay, so when you see 4, what should that be a hint? What? Very good. So a benzene is going to have an unsaturation of 4, right? And the reason for that is you have 1 ring, then you have 3 pi bonds. That is equivalent to 4, right? Every pi bond is going to give you unsaturation of 1. Okay, so very likely we're going to have a benzene ring. So if it's greater than 4, it means you have a benzene plus something else, okay? So now that we did that, now like he said, we're going to look at our IR. So cross out fingerprint, and then what we got here, right? What could this be representing? What type of bond? Double bond, so it's in our double bond region, and it's specifically probably going to be a carbon to carbon double bond. It's not super deep, the absorption is not super long, right? So that's what led me to believe that. In addition to that, the carbonyls would probably be a little bit further towards the 1700 region, okay? And this would make sense just because in our benzene, what do we have? Carbon-carbon double bonds, so that's correlating to that. And then we'll look on the left of the 3000, and what functional group can we see right there? Staring at us. Very good. This is our OH. So the oxygens that are in the molecular formula, one of them has to be the OH. Make sense? So that's all we can get from our iron. Not too much, but it tells us about our functional groups. Okay? So now we can move forward to the proton NMR, okay? Proton NMR. And what is that going to tell us about? Protons. Just going to tell us about the protons and how they're the skeleton of the carbon skeleton. So how the carbons are connected to one another, where the protons are located, what are they nearby, their environments, and so on. Right? So these nuclei of the protons, right? So that's a proton in the nucleus of the hydrogen, and it's spinning like this, right? It's processing. And you're going to hit it. So the reason why this is, so this is nuclear magnetic resonance. You're going to hit this with RF frequency. So radio waves. So that's how they differ, right? You're going to hit it with radio waves at some point in this process, okay? Before that, so we have all these hydrogens, and they're oriented in many different ways, right? It's random distribution, how they're oriented, okay? What you're going to do, you put it inside, you put your sample of the molecule, you put it inside a big magnet, giant magnet, okay? And that's going to have an applied magnetic field, okay? They call it B0. Okay, what that's going to do to all these nuclei, it's going to orient them in the same orientation as your magnetic field, right? A spinning charge is like a magnet, right? It produces magnetic field. So it's going to orient all of them in the same direction, all right? And this is when the RF frequency comes into play. You're going to hit it with radio waves. Okay, and you see all of these are pointing up, right? What you're going to do is if you hit it with a specific amount of energy, specific frequency, it's going to cause these to flip in an orientation that is opposite to the applied magnetic field. So you're going to get 2, right? put a little arrow like this, and at the bottom, so lower energy would be the ones that are in the same direction as our applied magnetic field right here, right? Same direction. The ones that are higher in energy are opposite, like that, okay? Do you guys know what this is called, what state it is? Alpha or beta? That's beta state, right? This is the alpha state. All right. So how does this even pertain to what we're doing up there, right? So the difference in energy between these two. This difference in energy, right? For the difference in energy, that is going to be pertaining to a specific frequency, okay? Remember that this equal that? So there's a specific frequency, and that is the frequency that we're going to be seeing up in our graphs here, okay? So every proton, every spinning nuclei is going to have something different, okay? And it's going to differ based upon the environment that those protons are in, okay? Whether they're de-shielded or shielded, right? So if something is de-shielded, right, it means it's next to an electronegative atom. And that pulls it more to the left, downfield. This is downfield. Okay, so that's what you have to pay attention to. Anything that's going further to the left, maybe it's attached to an oxygen, right? If you have a CH2 attached to an oxygen, it's going to be further downfield. All right, so let's do it. First thing that we're going to want to look at is what is called our integration number. This right here. So what is that piece? What does the integration number tell you? That it's a CH3, and I heard how many hydrogens. So that integration number is telling you how many hydrogens are on that carbon. How many same environment hydrogens you have, okay? CH3, just like that. And then let's move forward, right? We have a 1H. What do you guys think that could be? Hydrogen attached with a double bond. No, not necessarily. So I heard OH, and I think I heard someone say CH. And both of those are really good answers. For this one right here, it's going to be the OH, okay? Because our OH, the H has to show up somewhere, right? So we only have one H integration number across the spectrum, so that has to be the hydrogen involved in our alcohol, okay? Right? And that we knew that from the IR, okay? So that's our OH, and it's going to be a singlet, right? It doesn't participate in splitting, so that's another clue. And we're going to have, what about this one? What is that? CH2. Okay. And then what about the next one? Another CH2. And then what about this over here? So pay close attention to the region. Yeah. So the region that it's in, if it's between 6.5 to 8, that means it's the aromatic ring region. So those are the hydrogens that are involved in our benzene ring. Okay, and there's 4 of them. So I'm going to put 4 in a symmetrical fashion like this. Right? And so what's the substitution of our benzene? If there's 4 hydrogens, should be 2. Right? Because there's 2 leftover spots, and there's 6 spots, and 4 of them are hydrogens, so there's 2 leftover. Sounds good? Okay, so we got all our pieces down on the paper. That's what we know right now. So what I recommend that you do to avoid, missing anything later on is go back up to the molecular formula and count the number of atoms that are there and compare it to what you've written on your paper, okay? So let's do that. Let's see. We want to have 9 on the paper. Let's go and make sure that we have 9 written down. So that's 1, 2, 3, and then the benzene has 6. So we have 9. That means there's no carbonyls. There's no carbon that doesn't have protons. That's why it wouldn't show up. But we're good. We have 9. So what we want to do after that, what else do we have in our molecular formula that we don't have written down? Another O. Yes, you do not want to miss the other O. I think that other O is literally 4 points. It's crazy. So write down that O, make sure you got all of them. Now we got 2, so I put it in the box right over here, okay? So I have my pieces. Now, after we put everything that we know, we go back to the right, and we're going to go right to left and see how these guys are connected to each other. So what do we want to pay attention to?
Peaks.
The peaks, but what specifically? Like the signal, but the splits. I think that's what you mean. Exactly, yes. So you have a signal right here, and that signal is going to have splits, right? And what causes those splits? The neighboring hydrogens, exactly. So we have 3 splits. So what you got to know is this n+1 rule. That's so super important. So n+1, that's going to be equal to the number of splits that you see for that signal. And what is the n going to be equal to? The number of hydrogens that are on the adjacent carbon or atom, carbon, and how many are on that carbon, okay? The splits tells you about your neighbor. The integration tells you about yourself, okay? So, and these have to be not equivalent to the one in question, the proton in question, okay? So, all right. I think I'm double tapping. On neighbor, and those are not equivalent, not equivalent to the one in question. Like that you care about, the proton that you care about. What's another way to say that? To that hydrogen. Okay. And that's the only way they're going to split it. Okay, so what do we have right here? So we're going to want to do the number of splits minus 1, and that's going to tell us what's adjacent to it. So 1, 2, there's 3 splits, right? So the adjacent carbon has to have how many hydrogens? 2, exactly. So the CH3 should be attached to most likely a CH2, right? So I'm going to put on this arrow, you know, on this line 2 H's next to something that has 2 H's, okay? Then we'll move forward. That 1 H is an OH, okay? Don't worry about it. It doesn't tell you any splitting. It doesn't have any splitting. And then we'll look at the CH2. So what does it look like N is for that? This one.
CH3.
Yes, 1, 2, 3, right? So the number of splits minus 1, right? So you got 3. So that means this CH2 needs to be attached to the only thing that has 3 is the CH3. So I'm just going to right away put that connection. So I'm going to put all the pieces together, and at the very end, it's going to look like a mess. Then at the very end, I'm going to put the molecule and put it in the box, okay? So we got that CH2. So it's connected to the CH3, but from the left side, right, from the other side here, it should be connected to something that does not have any protons. Does that make sense? Right? Because there's 3. So for that reason, I'm going to ignore it for the time being. Well, actually, there's only one place that it can be connected to. Well, there's actually 2. We'll hold on it. We'll hold on it and move to the CH2, okay? Then other CH2. So the other CH2 is a singlet, right? So it's adjacent to no protons, right? No carbons with protons, right? And then we have the benzene. So what we want to do is pay attention to the locations of these signals, right? So the first CH2, and I'm going to try to highlight because I don't know if you guys can actually see. This CH2, right? Both these CH2s are pretty far downfield, right? So what do they need to be attached to if they're downfield? The electronegative atom, exactly. Right? So we can put it to that, and then the left CH2 from either side, right? It's not connected to something with hydrogens. So we can put it to connect to the benzene, right? And I'm gonna move my oxygen just so that it's not so far away. Put it right here, right? From the other side, I'll make it right next to this oxygen. And then we said the other CH2, so I'm gonna highlight it, but in a different color. That one, right, also is next to an electronegative atom. So that's the oxygen, right? And then our OH, the only thing left for the OH to be attached to would be the benzene ring, okay? So now that we have the connections made, what I want to do is go to the box and write it out, and then we'll check our work. So we had a CH3, and if we follow that CH3, it goes to a CH2, right? That CH2 is connected to the oxygen to make it more downfield, right? And then from the other side of the oxygen, it's attached to a CH2, right? And then that CH2 is connected to the benzene, like that. And then the benzene has the OH, that's all that's left. Okay, so on the exam, I recommend to you guys, go make sure all the atoms, right, are present. We have the 2 oxygens and we have the right number of carbons and hydrogens. So you're going to want to go to each one of these and count their splitting and make sure that it's appropriate.
So is that the final answer? Didn't we have a C double bond C in there?
Yeah, so the C double bond C, remember, what was our unsaturation? Well, so he asked, didn't we have a C double bond C in there, right? Because of the ring. So I drew it as a circle, but that's just another way of drawing the benzene, right? So those C double bond Cs are present in the benzene, not external to that, because you had the unsaturation of 4, right? So it's just the benzene, no other unsaturations. So you would want to go to every single atom, like you'd look at the CH3 that I highlighted, right? You ask yourself, okay, it should be connected to something that has 2 protons. Based upon the splitting, that looks good. Right? You go to that CH2, the one that's highlighted in purple as well, right? And you say that one should be connected to something that has 3 protons. From one side, that's the CH3. From the left side, it's connected to something that is making it all the way to the 4.0 region, right? A regular CH2 should not be there. So that looks good. And then the other CH2 is also, right, super downfield, and it doesn't have any protons on its neighbors, right, because of the singlet. So that looks good. And then our OH is what's left over. Okay? Do you guys have any questions? So her question was basically about why did we connect the OH to the benzene? Is it because it's just a singlet or something like that? So when you're doing it under these conditions, right? So these are not ultra pure conditions. These are normal conditions, okay? So what that means is your OH is not going to participate in splitting at all. It's not going to participate in splitting. And I'll talk about it a little bit more when we do facts. But it's not going to participate in any splitting, so it's always going to show up as a singlet. Your OH is always going to show up in these problems like this, right? But the thing is, that's a really good question, because I actually looked at the key for this, and there's 2 answer choices that she would say are acceptable.
Sabrina, it should be CH2OH on the benzene.
CH2OH.
Yeah, I think you just left it out.
No, so that's what I was going to mention. So there's actually 2 answers that are correct. I'm glad that he brought it up. So I have this right here. Oh, I see. I think I see what you're saying. Am I missing a CH2? No, we're good. So there's a second. Come here, Andres. I'll show you. So there's a second answer choice, right? So that's the one I put.
Oh, okay. Got it.
So that's a really good thing to mention, is that you could put what I put in the box, but you could also put another answer choice that would be marked correct. And I'll show you what that one is, okay? It's this. Like that. And then from the other side, that's what he was talking about, like a CH2OH, right? So this is an alternative answer, right? So you could have put either one of these. So if you were to go and check the same thing for this, right, go and check it back with the proton NMR, you would also get that it's correct. Everything lines up. So you can either put the CH2, and I'll highlight it for you guys. This CH2, right, can either go in that position next to the alcohol, or you can put it right there. Do you see it? There's 2 locations you could have put it, all right? Do you guys want me to go through the alternative answer and show you guys how it's correct? No? Okay. You're like, let's just get this done. All right, so that's your answer, okay? I just saw like a lot of blank faces staring at me, so. It doesn't matter if the OH has two neighbors. No, because these are not ultra pure conditions, right? These are normal conditions, so it's still going to show up as a singlet. Very good. So the benzene ring, yeah, so there is a ring current in the benzene as well, but it does actually de-shielding. Yes, or does it? Yes. Okay. Okay, let's do synthesis, okay? Do you guys prefer for me, like just by a raise of hands, do you guys prefer for me to do the way that's on the key or an alternative way, and then you guys can look at the key and see two different ways, or do you just want me to do what's on the key? Alternative way so that we can also see what's on the key and then see a different way to do it. Okay, just in case if, we blank and we don't think about it. So I'll do the other way. Okay, so it says that we can have cyclohexanol or 4 carbons or less, right? So I'm going to put my toolbox on the side here. Right, we can get it down to cyclohexanol, 4 carbons or less, and it says alcohols means alkenes. So I'll put that. 1, 2, 3, 4. And then we also are going to have that. And it's going to be less than or equal to 1, 2, 3, 4. Okay? So bless you. That was a cute sneeze. So how are we going to get started? So you want to look at the functional groups that you see in your final product. What do we have? What functional group? We see an ether, right? So we want to, at our last step, right, we're going to form that ether. So you can do that via an SN2 mechanism, right? SN2 reaction. Okay, so this is going to be SN2. So we're going to want to have a nucleophile. So you can pick whatever piece you want to be the nucleophile. So we're forming, which bond are we forming? This one, okay?
But why would you break it there?
Why would you break it there?
Yeah.
Yes. So there's different options. You could have also chosen to break it here, right? So it's because that oxygen is what's going to be the nucleophile to go and attack something. So that's why I broke it there. That's the last bond that we're forming, is the oxygen to the carbon, okay? And you can pick whichever piece you want. So I'm going to pick that side, okay? Right? And so when I do that, draw everything else the same, like that, right? And then where that oxygen now got attached, I want to make that a good leaving group, okay? So that's my bromine as a good leaving group. And then my other piece, right? My other piece, I want for it to be a nucleophile, right? So I have to decide, do I want it to be a strong nucleophile or a weak nucleophile? And that's dependent upon my alkyl halide and what I have there, right? So if I pay attention to that carbon that has the bromine, what degree is that? Secondary, right? So you actually, for this one, I would take the SN1 route, right? Because SN2 prefers primary, right, if we have this nucleophile. Right? If we had a nucleophile like that, right, that prefers to act as a base. So we're trying to avoid getting elimination. So I'm going to make it a nucleophile that will react in an SN1 reaction, right? So that just means a weak nucleophile, because this would go, leaving group would leave, form carbocation, and it would go and attach right where that bromine is. And on our arrow, what do we have to include? Heat, because we're doing an SN1 reaction. SN1 and E1 like heat. For synthesis, do not even worry about doing E1, okay? Just throw it out of your brain. for synthesis. So we got down to CH3, CH2OH, right? So we already got that piece down to less than 4, okay? So now we have to create this piece, right? We have we still have a lot of carbons that we need to connect. So we have to do carbon-carbon bond formation, right? So we want to get this down to an alcohol. So before that, we could have done a Grignard, right? We're going back to a Grignard. So here, how can we get a bromine on there? Exactly. You can do PBr3. This is secondary, right? So because it's secondary, you can do PBr3. That's okay. If it was tertiary, you cannot do PBr3, okay? Right? So I'll draw everything the same, except where the bromine is, now it's in OH, right? And we did the SN2 reaction, replace the OH with the bromine, right? So perfect, we got down to the OH, right? And now we can do what type of reaction to form carbon-carbon bonds? Very good. So I'm just right away, I'm gonna put the then H3O plus on the arrow so that I don't forget it. And then we're gonna wanna make the two pieces, right? You could do a Grignard attacking a carbonyl, but what else can you also do? Grignard attacking an epoxide, right? And I'm going to do that way just so that we avoid having 500 Grignards. You know, it's going to take forever, right? So I will break this up. Basically, the two carbons, these right there, that have that OH, that I want for it to be an epoxide before, okay? Just like that, that's one piece, right? And then we had carbon-carbon bond formation. So the other piece is that right there, okay? And that's going to be a part of our Grignard, right? That's going to be our Grignard reagent, right? But Mg and Br, that is a strong nucleophile, and it's going to come, these are basic conditions, so which side of the epoxide will it attack? Less substituted or more substituted? Less. Remember BLAM. BLAM? Right there. B, least, A, most acidic. A stands for or most substituted, sorry. So right? So a Grignard, these are basic conditions. It's going to go and attack the lesser substituted side, push electrons onto the oxygen that gets protonated by the then H3O plus, okay? Now, let's just do the Grignard side, right? I think that's, I guess, a little easier. So what are we going to put on our arrow to make a Grignard? Mg and ether. So we're going to put everything like we did before, but just make it an alkyl halide, right? So remove that magnesium, right? And then how can we get the bromine there? 1, 2, 3, 4 carbons. That looks good. So we had a four carbon alcohol. That's what the question wanted. And we use PBr3. That's a primary alcohol, so it's okay to do PBr3, SN2. Okay? Any questions about that? Okay, so now we do the other side. How do we make an epoxide? Like, what functional group do we have to have before? Alkene. Right there, right? And what do we have to put on our arrow? MCPBA, right? That forms our epoxide across that double bond. Okay, how do we make a double bond? So there's different options to make a double bond, right? You have E2, you have H2SO4 in heat, you have POCl3, right? I see a terminal alkene right? So I'm going to go with POCl3, right? Just to do something that's a little bit different maybe than what you guys see, right? And that's going to put the alkene at the terminal in there. So before that, what functional group do I have to have? An OH, okay? You have an OH, use POCl3, and that's going to give me the terminal alkene, okay? H2SO4 would not give me that. Okay, and so now I see another alcohol again, so why not do a Grignard, right? So we'll break this up into pieces again, and I like to do the epoxides to save myself some steps. So I always run out of room because I write so big. So we're going to get our two pieces, right? So we're going to have the epoxide piece like this, okay? And that's referring to that right there, okay? And then our Grignard, we're doing the same thing like we did earlier in this question. Our Grignard should be this, okay? So we got down to the epoxide, and then let's just make our Grignard. Right? That Grignard went and attacked the epoxide, broke the epoxide, gave you O minus. So what do we have to put on our arrow? Then H3O plus, right? Now we want to form the epoxide. How do we form an epoxide? From an alkene, just like that. And what do we put on our arrow? MCPBA. We got down to 4 carbons or less alkene, so that side looks good. I made this so big. Okay. So now how do we form our Grignard? What do we put on our arrow? Magnesium and ether. We have a bromine. So how do we get the bromine on there? We can go back to cyclohexanol. So I'll put the cyclohexanol for us. Right? And this is a secondary alcohol. So we can use either PBr3 or HBr, 0 degrees Celsius, ether. Right? Okay, and we got down to our cyclohexanol. Do you guys have any questions about this? We're good? Okay. Oh, I'll leave it there for a couple seconds. You can take a picture. Okay. Now let's do mechanism, okay? So we're getting like the big bad boys out of the way early, so hopefully the other stuff will not be as bad, right? So with mechanism, there is something that may be different between this, the final and the third exam, I'm not sure. But in the instructions, it does want for you to say, show, right? So it says, remember, it says, if more than one resonance contributor is possible, right? Be sure to show the more stable one. Okay? So you got to make sure to do that. So we'll highlight it. All right, so with mechanism, I recommend the first thing you want to do, compare your reactants to your product. Your reactant to your product. So what do we see that's similar and what do we see that's different between them? So in our reactant, so let's just look at product A. Let's look at product A. So what's similar between them? Right, so it seems a 5-membered ring, the ethyl group, and then also 5-membered ring with an ethyl group, right? So all the change happened outside the ring involving those two OH groups, right? right? Noting expansion. The other one, product B, right? You see a change between 5 to 6 carbons, right? And so at some point in forming that product, we're going to want to do a ring expansion, okay? But let's just focus on A. So with your first arrow, I think that's the hardest part, is deciding what that first arrow is going to be. And you want to look at your reactant, look what's on your arrow, and identify what's a nucleophile, what are the nucleophilic sites, and what are the electrophilic sites, right? So in our reactant right here, what are our nucleophilic sites? It's going to be the 2 OHs, right? The lone pairs on the oxygen. And then on our arrow, right, what's the electrophilic site, partially positive, is going to be the hydrogen, right? This is sulfuric acid, so it's going to be that acidic proton. So you can predict the first thing that's going to happen, it has to be one of those 2 OHs, right? One of them is going to go and attack that proton on the H2SO4, right? But then the question comes, which one do I pick, right? So if you're unsure of how to start, I recommend just pick one of them and see what happens, right? I'm trying to form product A. So for product A, I see that there's still this carbonyl oxygen there, right? That could be this oxygen that's right there in our reactant. So the one that's leaving or going away or vanishing somewhere is going to be the other OH. Okay, so that's the one that I'm going to use to do that first attack on the proton, okay? That's the one I'm going to protonate. Got protonated. Now, what is the charge on oxygen? Positive, right? And so now we have formed water as a good leaving group, right? So we want to get rid of that water so that we leave a positive charge on our molecule, and then we can have some movement, some rearrangements happening. So water can leave on its own just like that. And the carbocation that's getting formed is tertiary. So that's okay for the water to just leave on its own like that. No need for a hydride shift or anything like that. So the carbon that lost the water, right, that lost an electron, that is the one that's going to gain the positive charge. So that's why I put the positive charge there. Okay, so we formed a carbocation, right, and we see in our product, right, that you have a carbonyl that's forming, right? So that oxygen, with the lone pairs that I just drew, something has to happen there, okay? Like those electrons somehow have to come down, somehow, right? But it's not going to do that right now, right? Because we have 4 bonds to the carbon, right? And carbon can't have more than 4. It can't be pentavalent. So what we can do is we can somehow displace that positive charge and put it onto that carbon where the oxygen is attached, okay? So how can we do that? What type of shift? Hydride. Hydride shift it to get rid of that positive charge. So on the arrow, I'll write hydride shift. Okay. And we moved that hydrogen over here. So I'll also put it. You don't have to show it. So we moved it over there. So that carbon that it came from now has what charge? Positive charge, right? So now we formed what we were trying to get. So we were trying to get a structure, right, where we can have these lone pairs. They can come down, right, onto where that positive charge is and displace that positive charge. This is resonance. So I'm going to want to show brackets. right? You form a carbonyl, still attached to an oxygen, still attached to the hydrogen. So now what charge does the oxygen have? Positive, okay? This is resonance that's happening here, right? Same atoms connected to the same atoms, right? But what's different here is the electrons now have gone into forming that carbonyl. Okay, and isn't that what we're trying to get up there? So our last step, right? The only difference between this resonance structure and our A product is the proton, right? So we want to use something to come deprotonate that and make it neutral. So what do you guys want to use as our base? So the conjugate base to the sulfuric acid, we can use that. And come down, put the electrons onto the oxygen. That gives us our A product, right? What else could you have used? What else could you have used as a base? H2O. You could have used H2O because you formed H2O as a leaving group. So you could have used that as well. Okay? Any questions about that before we go to the next one? No? Okay. And remember the question said, be sure to show the more stable resonance contributor, and that is going to be this one, right? All the octets are fulfilled. So now we need to somehow form this B, okay? And what's the difference we said between our reactant and B is that we've done the ring expansion. Right, so we have to get back to a carbocation intermediate of some sort. So I'm just going to put a redraw of my initial reactant, okay? So, and I'll make sure to indicate that this is the same thing as what I'm given. So redraw, and I'll put exactly what the problem gave us. Right? Just like that. So now, what do we want to do? Which oxygen do we want to go attack? The sulfuric acid. So we used the other one last time to give us that carbocation. Right? But if let's use the other oxygen, right? Because we see a ring expansion happening, and that ring expansion, if we pay attention to our product right here, right, you have 1, 2, 3 carbons coming outside the ring, right? So that means there's going to be some movement on that side, if I highlight it right there, right? There's 3 of those carbons, and so those are the 3 that are going to be outside of our ring now, okay? So what I want to do is use this oxygen to go and get protonated. So I'll rewrite the sulfuric acid like that, show the protonation. Alrighty, so that oxygen got protonated, right? So now it has a positive charge. And what do we want to do? Water off. Kidding me. So what we want to do is that water is now going to leave. Okay? The reason why we want to do that, we want to form the carbocation intermediate. Right? So that left, and we formed that positive charge right on that carbon that lost the electron. Okay? Now we want to do the ring expansion, right? So let's see how we can do that. what we're gonna do, and I'll highlight the bonds. This one right here. All right. So we want to pay attention to which bond is the one that's breaking, right? Basically, is it gonna be the one I highlighted or this other one I'll highlight in the same color? Which one of those two, right? So let's see. We want to get it down to 6 carbons, right? So let's try this one right here and have it go attack that positive charge, okay? And I think it would be best for me to probably number this. Okay, so right now what I have written down is just the ring. So I'm going to zoom in a little bit, right, just to make sure that we're numbering this correctly. So we have 1, I wish I made it a little bit bigger. 2, 3, can you guys even see that? 5, right? And then we're gonna have the 6, 7, 8, 9, right? And then we have that ethyl group coming off of number 1. So I'm gonna number 1, right? That's my number 1 that has the ethyl group, right? And then number 1 is still gonna be connected, right, to number 2. Okay. And number 2 is still gonna be connected to number 3. Okay. And number 3 is still gonna be connected to number 4. And number 4 has a OH, right? Still, nothing happened to that OH, right? And now you broke the bond between number 5 and number 4, right? So it's like a door hinge and it swings, right? And it goes, that number 5 goes to attack number 6, okay? So number 4 now, right, it's no longer bonded to 5, right? It's still bonded to 6. So I'm going to put 6 right there, right? And then now we formed a bond between which 2 atoms? 5 and 6. So that's my number 5. That now we formed that bond. So I'll highlight the bond that we formed. And it's that one. Okay? So basically 4 and 6 are still connected to one another. Okay? And then now our 6, it was still connected to, we don't want to forget, it was still connected to a 7, right? Which was connected to an 8, which was connected to a 9. Okay? So I'll indicate those. And now you want to ask yourself, which carbon, which number carbon has a positive charge? 4, yes. Because 4 is the one that lost the electron, right? So 4 is now going to have a positive charge, right? But in our product, basically everything so far, it looks very similar to our product. What's the difference is that we have an OH and we want to make that OH into a carbonyl, right? So we're going to do the same thing that we did in the previous mechanism, and we're going to show the resonance, put the brackets to show the resonance, and the electrons on that oxygen are going to come down, rid of that positive charge, and displace it now. That's your ring. Number 4 now is going to have this carbonyl with the hydrogen attached, and what charge is the oxygen now? It's going to be positive, right? And then your number 6, of course, is still going to be connected to all of those guys, right? So which resonance contributor is more stable, the A or the B? A? Are you sure? So B fulfills the octet. but A does not. So A, you have that carbocation, right? So that's very unstable. So it's more stable to have the octet fulfilled, even though that oxygen has a positive charge, right? And that's really important for facts. So try to trick you. So that's a resonance structure, and that one is the more stable one. So we showed it, we'll get full credit. And now we want to show the deprotonation. So what are we going to use for that? Let's just use H2O, right? Goes and attacks that, and the electrons go onto the oxygen, right? And that forms our B product with the carbonyl, okay? Do you guys have any questions about that? About the ring expansion, about why, something? Y'all are all good? Y'all are all gonna get A's? Hope so. Fingers crossed. All right, so no questions? Zoom. All right. All right, so we're ready to do reactions. Let's do reactions, my favorite part. I love reactions. Okay, let's get started. So number one, we have these vicinal diols, all right? And what is their relationship to one another? Like, are they syn or are they anti? Syn. Okay. So when you have these OHs and you have them syn to one another, and you have this specific reagent right here on our arrow, right? Periodic acid, right? What's going to happen is you're going to have, it's already kind of drawn in there actually, you're going to have cleavage across that carbon-carbon bond right here. You're going to have cleavage down that, and it's going to oxidize it at the same time, okay? And I'll show you what I mean by that. So I'll put number one here. Ring, nothing else gets touched, okay? What does get changed, you guys, is those carbons that have the OH, right? Now they're going to be carbonyls, right? They're getting oxidized, right? And you have a hydrogen coming off of the top one, right? Because there was a hydrogen here, okay? And then the other one, this one right here, also going to become a carbonyl, right? But it's going to be a ketone, right? Because you have this CH3 group there, okay? So you got to really take note of the fact that the aldehyde, it's stopping at an aldehyde, okay? It's not oxidizing all the way to a carboxylic acid. So you can relate this, it's similar but different, but similar to ozonolysis, right, of an alkene, of a double bond, not of a triple bond, double bond. Where with I always call it ozonolysis, but I know I don't know how to say it. Ozonolysis, sorry. So ozonolysis, it's similar to that in the sense that you're going to stop at the aldehyde, okay? And I have a really cheesy way to remember this, right? Because there's a lot of reactions. So just imagine, right? It kind of looks like haya, right? Like haya, right? So you go like this, haya, and you cleave the bond. Okay? So just remember haya, and you cleave the bond right there, okay? Hopefully me doing this will make you guys remember what's going on, okay? So haya, and it cleaves that carbon-carbon bond. Okay? Now, what we got going on, so number 2. We have H2 and Ronnie nickel, okay? So whenever you see H2, you need to be thinking that this is a reducing. We're doing a reduction, right? So this is a reducing agent, right? And this wasn't too bad for me to remember because I have a friend named Ronnie, so I just remember him. And I remember, that, I don't want to throw shade, but he's not very selective, you know, so he gets around with everybody, you know. So I just remember that, you know, he's not that selective with who he picks. So I hope he's not going to see this, but I just remember that, and that helps me to remember that Ronnie he's going to reduce everybody, you know. So that's what's going to happen here. So if we had an alkene, Ronnie's going to reduce the alkene, and he's going to reduce the carbonyl, right? And he's going to reduce the aldehyde, all of them. So just remember Ronnie. Going to reduce them to what? It's going to reduce it to an alcohol, okay? One, two, and then you got a CH3. You got a CH3 still coming off, okay? Okay. Good in the number of carbons. So now, number 3, we have H2SO4 and heat. You guys have seen this one before, right? This is just dehydration, acid-catalyzed dehydration of an alcohol, okay? And we have 2 alcohols over here, right? Let's deal with the bottom one first. We're just going to go straight into our box, right? And you're going to protonate that oxygen, right? And then it's going to leave, and you're going to form a carbocation. And then after that, an adjacent proton, right, is going to be abstracted, and those electrons will fall in and create the double bond. And it's going to give you the most substituted product that it can, okay? So you look adjacent to the OH, right? So you got this way, right? And then you also have this way where the double bond can form. And the first way that I drew, the first dotted line that I drew, if we form the double bond there, right? If we form the double bond there, what is our substitution gonna be, right? It's gonna be 1, 2, so it's gonna be di-substituted. Does everyone see that? It's kind of hard to see, right? If you form, I'll put a highlighter, okay? If we put the double bond there, we're going to get a di-substituted product, okay? There's going to be 2 carbon groups coming off of it, right? Versus if we put it up there, right? What is our substitution going to be? It's going to be mono substituted, right? You're only going to have 1 carbon group coming off of that double bond, right? So which way is it going to pick? It's going to go the way that gives you the more substituted product. So that's going to be the di-substituted product, okay? So I'll just put that part, and then we'll deal with the other alcohol afterwards. So this is the CH3. The OH had left as water, and we got this, okay? Now, let's deal with the other side. So what degree alcohol do we have? Primary, right? So we have a primary alcohol. So when we're doing this, right, you're not going to be able, so when this alcohol gets protonated, the OH gets protonated, it's not going to be able to leave as water on its own and form a primary carbocation because it's very unstable, right? So what's going to happen is you're going to have a hydride shift would happen at the same time as that leaving group is leaving, right? To push it, propagate it to leave, okay? So for that reason, we're going to want to put our double bond more internalized, right? And I feel like a lot of people might have questions. So if you have questions about this, just ask and I'll explain it to everybody. And we're going to put our double bonds right here. Okay, it looks like I did 2. Right, we're going to put our double bond right there. Can y'all see it? Yeah. Okay, so, do you guys have a question about that? Any questions, or you guys got it? I can explain it again if you want me to. No? Can you explain it again? Yes. So right here, what I was talking about is this OH. This goes and gets protonated, right? This is dehydration of an alcohol, right? Acid catalyzed, gets protonated, and what you're gonna form is a positive charge on this oxygen. Then what's gonna happen? It's gonna leave, right? It's gonna wanna leave, but if it leaves, it's gonna form a primary carbocation, and that's not stable. That's not stable enough for that to readily leave on its own like that. What it needs is the propagation of this hydride to come and push it in order to jump off, okay? And when it does so, that will displace the positive charge. Instead of being on the end of the molecule like that, it's now going to be on this highlighted carbon, okay? And because of that, you're going to get the double bond to form right there. Do you see that? It's going to grab an adjacent proton and form right there. Does that make a little more sense? No? Yes? Okay, thank you. Because some people are looking at me like, and I'm like, oh my gosh. Okay, so that will be your answer. And if you have further questions about that, like just make sure to ask, or you can ask me at the end. I'll do it again. Okay, so let's do number 2. So we have lithium aluminum hydride. Is this an oxidizing agent or a reducing agent? Reducing, because it has all these hydrogens, has all these hydrides. It's a source of hydrides, okay? And is it going to be strong or is it going to be weak? Boom. Think of Layla. We have this girl named Layla, and she's psycho. She's crazy. She's just going to attack everything, right, in her path. So that means that even in ester, even in acid chloride, they are going to react with lithium aluminum hydride, with Layla. Okay, so that's what we have here. We have an ester. So you have the lithium aluminum hydride, positive charge on lithium, minus charge on aluminum. Okay, and your hydride is going to come, attack right here. Pi bond becomes lone pair. You're going to get a, do you guys want me to draw the mechanism? I can go straight to the product. If you guys know it, we'll move straight to the product. Product. Okay. So I'm going to show a pseudo reaction or mechanism. That's going to go and attack, right? Carbonyl, right? Pi bond goes onto the oxygen. They come back down and reform the carbonyl, right? Push off the leaving group, okay? So that's what I'm going to put so far. Everything's same. Now we formed an O minus because our leaving group left. Right? We basically reformed that carbonyl, right? And we have a hydrogen attached there, okay? And after that, right, lithium aluminum hydride again is going to come and attack that carbonyl, okay? So same idea. Again comes an attack, right? Push the electrons. My heart. I have a charger. I have it, but I hope I can plug it in at the same time. As long as our recording is still going, we're good. Where is it? The tension, you guys, the tension. What is it? Bernardino? Oh, there it is. I found it. Don't be alarmed. Ay. Boom. Steady hands. Yay, we're good. Okay, false alarm, that was close. Okay, so let's continue. What were we talking about, Layla? So these electrons, they come onto the oxygen. come onto the oxygen, right? And you get O minus, okay? And then, so now that we got that part, just put the O minus, right? We attach another hydrogen there to that carbon. And then after that, right, we have the nature of plus. So what's that gonna do? Protonate, both those guys. Protonate, boom, and boom. Just like that, okay? The eraser is huge. Okay, make sure I didn't erase any carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we formed these two alcohols. All right, and now we use NaOCl, which is just household bleach. So is it oxidizing or reducing? Oxidizing agent, and it's very selective, right? Not like our friend Ronnie. It's very selective. What it's going to do, only it's going to oxidize the secondary alcohols, okay? Secondary alcohols, and what is the only other exception that it will also oxidize? Remember this? If you have an OH that's on that benzylic position, it will also oxidize that position, right? Even though it's primary. That's the only exception. So what do we have here? We have one of these alcohols is secondary. So I'm going to reduce that one. So we got the CH3, and that's now going to be a carbonyl because that's the secondary alcohol. And it's still going to be connected all the way to the oxygen, that OH, and that one gets left untouched. Don't touch it, and it's good, okay? Any questions? Okay, so let's move forward. So what do we have going on here? We have NaI and acetone, okay? And let's look at our alkyl halide. What degree alkyl halide do we have? That's the first thing you want to do, is to look at the degree of the alkyl halide, and that will direct you in a certain direction, okay? Between these guys. The big four, okay? So our alkyl halide over here is, it's secondary, right? Secondary alkyl halide. So can that knock out any of those options? No, unfortunately no. So all four of them are still, they can be picked. And we have basically iodide, right? So I minus being balanced out by the Na plus. And then we also have acetone. So is that protic or aprotic solvent? Aprotic, very good. So given that information, which one of those big four are we going to pick? SN2, exactly. We're going to go with SN2. Okay, that's the one we're going to pick. And we picked that because of the fact that I minus, strong nucleophile, it's one of those in the mnemonic, the bro, I really suck corn nuts mnemonic. I, that's iodide, and acetone, aprotic solvent, okay? So we're going to do an SN2 mechanism, a reaction, right? And it's all going to happen at the same time. It's concerted. Let me draw the other side all the same. Right? This is the carbon here that I highlighted. That's the one that's going to come and get attacked from the back side by the I minus. Okay? All at the same time. Boom. Attacks from the back. Inverts the stereochemistry. Bromine is going to leave. So you're going to put, the leaving group was on a wedge. So now we're going to put it on a dash. Right? And that's going to be the iodine that's connected, okay? And our hydrogen that was on a dash is now gonna be on a wedge, okay? SN2 100% inversion is what just happened, okay? Okay, so now what do we have is we have this ethoxide, okay? So whenever you see ethoxide, you should be thinking that this is a base, right? Let's go and look at our alkyl halide. Remember I told you the first thing, just to be sure, always check that alkyl halide and check the degree of it, right? So we have 1, 2. So that iodine, that's our leaving group. That's our good leaving group, right? So it is a secondary carbon, okay? So that, for that reason, we can't rule it out and say it's just, if it was primary, we're going to say it has to be SN2, right? But it's secondary, so we still have all these options. So what we want to look at next is our reagent. We said it's strong. How did we know that it's strong? I knew that it was strong because it has a full minus charge, right? Full minus charge makes something strong. If it was just ethanol, OH, then it would be weak, okay? So it's strong because of the minus charge, and it's going to be acting as a nucleophile or a base. What do you guys think? So it's going to be acting as a base, okay? So the only time where you'll see this ethoxide, and this is particular for Dr. Bean. Miljonic doesn't seem to really care about this, but Dr. Bean cares about this, and the only time the ethoxide will choose to act as a nucleophile is if the alkyl halide is primary. It will take SN2, right? If it's secondary or tertiary, anything that's not primary or methyl, right? So it's going to act as a base, okay? So if it's going to act as a base, then which one of our big four are we going to pick? We got to cross out SN1 and SN2, right? It's strong, so we're going to cross out E1, so we're going to go with E2, okay? That's how you go about the process of picking which one. So we chose E2, right? And a base, right? A base is going to come and it's going to deprotonate an adjacent proton, okay? And so that's adjacent to the leaving group. So it could be this one, or it could be one of these. They're not being shown, but they're there. One of those guys, okay? Now, in terms of stereochemistry, you have to pay close attention that E2 wants the stereochemistry of that leaving group. The leaving group to the proton has to be anti-coplanar, okay? Or trans-diaxial, because we're talking about a ring, right? So trans-diaxial, you have to really pay attention to this thing to pick which hydrogen is going to be abstracted. So trans-diaxial is the proton that gets abstracted to the leaving group that leaves. So it's I here, but I'll just put leaving group, okay? They have to be same plane, opposite directions, okay? So we'll assign the iodine, right? If we want it to be axial, we'll put in parentheses our iodine is axial, okay? That means that hydrogen right there must be what? Equatorial, alrighty? So then on the adjacent carbon that has those two protons, right? One of them is going to be axial, one is going to be equatorial, and the one that's going to be axial is the one that's on the wedge, because it flips every time you go around the ring. It's going to flip, right? So if the iodine, right, on a dash is axial, on the next carbon, right, the wedge is going to be axial, okay? It flips. So then that means that other hydrogen, no. This other hydrogen is going to be equatorial, okay? So we have one that's axial, that's good. Let's check on the other side, right? Let's check on the other side if we have a hydrogen, if we have one that is axial to our leaving group. So we said that our dash, right, the iodine is axial. So that means if you go up to that next carbon, the one that I'm circling kind of right now, right, that one, if it's on a dash, that means that has to be equatorial. It was a hydrogen, right? Okay. And this was a CH3. Oh, thank you. So I need to make the eraser a little bit smaller. Ooh. Okay. So our hydrogen here is equatorial. So that's a problem, right? Can we abstract it? No. The hydrogen and the leaving group have to be trans-diaxial. And we found that hydrogen is equatorial. So that's why we can't do it, okay? So that means where is the double bond going to form? it's going to use the other, so I'll highlight it in purple. It's going to come and abstract this hydrogen because it's transdiaxial, okay? And then our double bond is going to form right in between that hydrogen and the leaving group, okay? So we'll put the ring just as it was, the upper carbon left untouched, right? So we got a CH3, still we have that equatorial hydrogen, right? And then the iodine had left, right? The base came, abstracted the proton, right here, push the electrons down, form the double bond, and iodide will leave. Okay? So our double bond forms right there, and that's it. Okay? Any questions about that? Just make sure the leaving group and the proton are transdiaxial to one another, okay? No matter if the other side would give you a more stable product. In this instance, right, the other side would give you the more stable double bond, right? But it's not going to form because they're not transdiaxial, okay? Okay, so we have potassium permanganate. Conditions are warm and concentrated. So these are harsh conditions, right? And notice there's a lot of oxygens, right? So what type of agent is this? Oxidizing or reducing? Oxidizing, exactly. You have your functional group in the molecule is a double bond. So that's where the reaction is going to take place, right? And just like Haya, it's going to cleave it in the middle, right? Here, okay? Cleaves it right there, and you're going to add two little carbonyls, O and O, just like that, okay? So I'm going to redraw this, and you see, notice how this is a symmetrical molecule, right? So both pieces are the exact same. So that's our piece. And then are we going to leave it as an aldehyde, or are we going to oxidize it even further to the carboxylic acid? Carboxylic acid. So warm, concentrated. This is very harsh conditions, very strong. It's going to oxidize it all the way to the carboxylic acid, okay? So you've got to put that OH there. Not like ozonolysis, whatever. Ozonolysis. So, girl, it's so hard for me to say for some reason. It's just one of those. All right, so number 2 is a new reaction in a sense, and this was not tested over in the third exam, okay? So you see an alcohol and non-aqueous acid, and then you see a carboxylic acid, right? And all that's going to happen here, you are not responsible for the mechanism. In Orgo 2, yes, but now don't worry about it. It's pretty easy to get to where the product is. All you do is you take the alcohol and you take the carboxylic acid and you whoop and push them together. Just squeeze them together, okay? So I'll show you what I mean by that. You get this, redraw the carbonyl exactly as it was. Now connect it to whatever is remaining on that alcohol, all right? So the O, CH2, CH3, and you form an ester. So what's the name of this reaction? Fischer esterification, right? So as the name tells you, you're forming an ester, okay? And you need non-aqueous acid in order to do that. So that's why it's just H plus, and they put a slash. It's at the same time. This is not a then H2O plus, okay? I want to make that distinction. And this is a condensation reaction. What does that mean? You're just removing water. In the process of these coming together, you're removing water, right? That's why you want this to be non-aqueous. Okay, now we have, in our step number 3, we have what type of reagent? Grignard. There you go. So what's going to happen, it's a strong nucleophile, going to come, boom, attack right there, carbonyl, carbon, push the electrons onto the oxygen, they're going to come back down, right? Then this is a good enough leaving group. That OCH2CH3 is a good enough leaving group to leave. Okay? So when it does that, you basically reform the carbonyl and make an attachment. So on this side here, I'm going to put our intermediate. You reformed the carbonyl, O minus CH2CH3, ethoxide left, and now you have the attachment of whatever that Grignard reagent was, that alkyl part of it, which for us, it's the benzene ring, okay? You reform the carbonyl, right? And after that, right, notice this excess. That should be your clue that this is happening more than once, okay? So let it remind you that. And you reform the carbonyl, so a Grignard is going to go and attack anything that's electrophilic, right? So it's going to do the same thing. It's going to go and do it again, right? Boom. Go up onto the oxygen, right? It stays there, doesn't come back down because you don't have a good leaving group. And it just attaches another benzene ring just like that one. So I'll do that. We got an O minus up there. We have the attachment. This doesn't really look like a benzene. Let me fix it. All right, so you have the attachment of this benzene ring twice, and what's left over is the then H3O plus. So what are we gonna do? Protonate the oxygen. Exactly. Okay? Any questions about that? Happens twice because that is a good enough leaving group to leave. Okay? The O, CH2CH3. So let's look at the next one. What do we have? So we have Br2 in light. This was learned way back first exam, right? So it's written excess over here. This is a free radical halogenation where you're going to be substituting a hydrogen with a bromine, okay? So let's rewrite what we have there. And the most substituted position is going to now gain a bromine, one bromine, because of the excess. Just like that. Okay? You cannot put the bromine at, for example, you cannot put the bromine up here. Okay? It has to be in that position, okay? Because that's the most substituted position for the free radical intermediate that forms. That's the most stable one because it's tertiary, okay? Remember the trends? So we're going to get our bromine and it's going to go right there. Now, that was our step number 1. Now we're going to do our step number 2. Okay, so we have CH3CH2OH. Okay, so is this strong or is this weak? It's weak. Very good. I asked that first because, right, so if it was O minus, it'd be strong, right? Now that we established that it's weak, this can act as either a nucleophile or a base, right? So E1 and E1 and SN1, right? They have the same conditions, right? They're both going to be something weak, right? Like this ethanol, and typically you'll actually see it with heat. Here she didn't put that, but you'll see it with heat as well. All right. So you're going to get a mixture of products. You're going to get some SN1 products, and then you're also going to get some E1 products, okay? Because we established that this can act as a nucleophile and can act as a weak base, okay? So it gives us major, minor, minor. So always, which one is going to be your major product, SN1 or E1? Ooh. I heard all SN1 and then someone said E1. So it's SN1, and Dr. Miljonic may not care as much about this, but with Dr. Bean, she's very adamant that it is SN1 that is the major product between the two. Okay? You'd have to increase the temperature to an insane amount for it to be the E1 to go up to the major product. So we're going to put SN1 as our major, okay? And what happens there is substitution. You're going to form the carbocation intermediate, right? And then that group is just going to come and substitute the bromine. right? So you have 2 carbons, right? So just O, CH2, CH3. And of course, this is racemic, meaning that you have some S and some R, right? A little bit 50-50 of both, okay? But here we're not going to show the stereochemistry. They're not asking us to show it because we were not given it, okay? So that's what we're going to put for SN1 product, which is our major, okay? Now we want to do the E1 and find the 2 products for that, all right? So E1, we have a base, right? It's weak, and it's going to come after that carbocation intermediate was formed. You're going to go and abstract one of those adjacent protons. The electrons will fall down, and you're going to form a double bond. So both of these are labeled as minor, right? So we're not going to care too much about which way the double bond goes, which one's major in comparison between the 2, but we're just going to show that a double bond is going to form adjacent, like in between the hydrogen and the bromine, right? That's your first double bond is going to form there, and then your other double bond is going to form over here, okay? Right in between. So these are both minor boxes, so we're not going to worry too much about which one goes where. We're going to put that double bond up top, right? And in the other box, we'll say that the other proton got abstracted, and we put the double bond inside the ring, okay? So between these 2, which one is major? Like, which one is present in more amounts? A or B? It should be A, right? A is the more stable alkene because it is tri-substituted versus the other one is di-substituted, okay? So between the 2, that A is your major, but both the boxes say minor, so we're not going to worry too much about it, okay? Sounds good? Okay. So for this next one, interesting. So this next one, in number 1, it tells us PTSCl pyrimidine, okay? So p-toluene sulfonyl chloride, all right? It's a mouthful, but all it's going to do is it's going to replace the OH, right? Is OH a good leaving group? No, right? So OH minus is very unstable, so it's not likely to leave. It's not stable on its own. So what we want to do with this one is we're going to replace it with something that is a good leaving group, okay? And that's our OTOS, okay? So I'm just going to redraw everything the same. Right, wedge and dash, all that stuff is going to be the same. All right, and we're just going to replace that hydroxy with OTOS, okay? So this right here is not an SN2 mechanism, all right? It's because it's not SN2, that's why I didn't change the stereochemistry, right? That's why I didn't flip that chiral center. I just put the OTOS exactly in the same orientation that the hydroxy group was, okay? Because this is not SN2. That's important. For the next part. Let's see what we got. So we have this methoxide, okay? And what this methoxide is, so I want to ask you guys, is it strong or is it weak? Strong, right? So it is a strong base. Let's go to our alkyl halide, right? And let's confirm that it's not primary, okay? If it's secondary or tertiary, then we know that an E2 mechanism is going to happen. So we go over here, that carbon over here, we see that it's attached to 3 carbons, tertiary, perfect for E2 to happen, perfect. So that's what we're going to have happening over here. Ignore the solvent. right? It's the methoxide that's going to go and react, okay? And it's going to act as a strong base, right? And so what, in terms of stereochemistry, what is important for E2? Transdiaxial, if we're talking about a ring, okay? So anticoplanar, right? So this is where it gets a little tough to explain it. But what you want is you want your leaving group. Remember, your leaving group, and your hydrogen, right? The one that's going to get abstracted to form the double bond. You want for them to be anticoplanar to one another, right? Are they anticoplanar right now? No. They're actually syn, which is not what we want, right? So what we got to do is, this is a sigma bond, single bond, right? We can rotate it. There's free rotation. We can rotate the left side, right, in order to get it so that that proton, this one right here, so that that one is anticoplanar to the OTOS. That's what we have to do. And this is really hard for me to visualize, show you guys from this view, from this angle. But you can imagine, like, even if you want to try it on your own, and if you were to take like three pens like this, right? And we're looking at, how am I going to do this? So we're looking at that carbon right there, okay? And what we have, I'm like you guys, right? You're looking this way on the paper, to the paper. And what you have is the hydrogen is going down like this, right? And then you have a CH3, CH2 that's on a wedge. So that means it's coming towards you. So it's going like that, towards you guys. And then we have a CH3 that's on a dash. So it's going into the paper, towards me, right? So you have it like this, okay? And all that we're doing is like a wheel. I wish I had another person, but it's just like a wheel, and we're rotating it like that, okay? Think of a wheel and it's rotating. And when we do that, we're going to keep the one with OTOS exactly the same, okay? The carbon with OTOS stays like this, right? You have the CH2, CH3. You have the CH3 on a dash. This, nothing happened. You rotated that one. So our hydrogen would go anticoplanar, right? And then the other two groups are now reversed. So whatever was into the page, right, whenever we flipped it around, it's now coming out of the page towards you guys, okay? So what was that? The CH3. Okay? And then the other thing that was attached there that was on the wedge, after we rotated our wheel, now it's going into the plane. And so that is our CH2. So I'll put that on the dash now. Okay? And the stereochemistry for that is very important. And even more so important for our next step when we use the MCPBA. But we still haven't even created the double bond. That was just me flipping it, right? So let me do that now, right? Now that we got them anticoplanar, and we're doing E2. So this OTOS would have left. Let me show the strong base. It deprotonates that, right? Electrons go onto that sigma bond. OTOS is going to leave like a good leaving group. And we form the double bond, right? So this is kind of like in parentheses. So we got a double bond, right? And so what's on the dash, the two things on dash need to be going the same direction up from our double bond. Like this. Okay? The two things on wedge need to also be facing the same direction in our double bond. So that's this CH3, right? And this other ethyl group. like that. Okay, does that make sense? Everything on wedge, the two things on wedge face same side. Everything on dash face the other side together. Okay, so that's important for when we do step number 3. So step number 3 is going to form what? The epoxide, right? So we'll take the double bond, right? And the 2 carbons that are part of that double bond, we'll take that. Those are the 2 carbons that are now going to be a part of the epoxide, right? And now what's connected to those carbons is important, how we show their stereochemistry, right? So the ethyl group, the CH3CH2, let me highlight it here with a different color. This guy. And also this guy need to be going in the same direction because they're on the same side, right? So I'm going to put both of them on wedge. Like that, okay? Now let's do the other piece, another color. These are on the same side, so I want them to face the same direction because the stereochemistry is conserved. So I'm going to put dash, CH3, dash, ethyl, like that, okay? Do you guys have any questions about that? No? Good job. Okay. So now number 7, what do we have? So we have these vicinal dihalides. So the NaNH2 is going to give us what? Double bond or triple bond? Triple bond, okay. And is it going to give it to us internal or terminal? Terminal, boom. Very good. Well, I'll draw this quickly. Oh, boom. So how many carbons we have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? We got it terminal, and there's also going to be a then H3O plus step, right? So we got that carbon there is protonated, okay? Because of the then H3O plus. Now what do we have? We have Ca2BH, hydrogen peroxide, basic conditions, right? And this is just hydration of the alkyne. You're adding the components of water across the triple bond. What that means is one of those carbons is going to get a carbonyl. That's one carbon. And the other carbon is going to gain 2 hydrogens, okay? So, and it matters which one, right? So with Ca2BH, is this going to be non-mark or mark? Non-mark, exactly. So that just means the functional group is going to go onto the lesser substituted carbon, which is the one at the very end. Like that. Okay? So that means that this carbon right here, 1, 2, 3, 4, this carbon, the green one, is analogous to the green one at top, and then the purple one is analogous to this one, and you form an aldehyde, okay? Think of, I have a little trick for this. Think of Sia, like the singer, swinging from the chandelier. If you flip this sideways, kind of looks like a dangling chandelier, right? Think of it that way, okay? It's going to be at the very end, the aldehyde. So that is for 2/3. We got to include them together. Now we have step number 4. Step number 4, is this a reducing or an oxidizing agent? Reducing agent. So there's source of hydrides in there, right? So that's going to reduce the aldehyde. It will also reduce ketones, okay? No esters and no acid chlorides. So we take that purple carbon, get it reduced to an alcohol, okay? Sounds good? Now, our step number 5, POCl3. We use this in the synthesis, remember? So what functional group are we going to form? Terminal alkene, 100%. Just like that. When we count the number of carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, sounds good? Let's do number 8. So we have this acetylide anion, right? So is that going to be a nucleophile or an electrophile? This guy. Right. Bye, no problem. So it's going to be a nucleophile, strong nucleophile, negative charge, excess electron density. It's going to go and attack the only thing on our molecule that is partially positive, right, which is the carbonyl carbon. So we draw this. This goes, attacks right there. Electrons go onto the oxygen. Just like that. We got an O minus, right? And we have the attachment. We have carbon-carbon bond formation here. Right here, that's the bond that got formed. That's going to be connected to the carbon that has the lone pair. And that's still going to have a triple bond to carbon with the CH3. Okay? Sounds good? Are we done with that one? Protonate, very good. So we're going to protonate that O minus, and we're going to end up with an alcohol, okay? You'll see this in the synthesis a lot. A lot. All right, so that's what we're going to get from that step. And then we have H2PDBASO4 quinoline. So what's another name for that? Lindlar's catalyst. Right, this whole complex. So in synthesis, you can just write Lindlar's catalyst. You have H2, source of hydrogens. So we're going to reduce, not oxidize. We're going to reduce. And what are we going to reduce on our molecule? Alkyne. So let's put the arrow since this is our last step. Just like that. And we have the alcohol still, right? Nothing happens to our alcohol, okay? Still connected there. Carbon to carbon, we reduced it to an alkene. We did not reduce it all the way to an alkane, okay? What would you need to do that? Does anyone know? To get it all the way to the alkane, you're going to need just H2 with a metal. Very good. Here, H2 with Lindlar's catalyst is going to let us stop at the alkene, okay? And what is the stereochemistry going to be? Just like grass, it's going to go the same side, right? Just think of grass. Or whenever you have these complexes of metal, right? Whenever you have that solid metal catalyst, always it's going to be same side, whatever you're adding those hydrogens. So that means we're going to get, how do I want to draw this? We put one like that, right? You still have a CH3, right? And from the other side, now you're going to have the hydrogenation. So you're adding 2 hydrogens across that triple bond. Sounds good? Same side, syn. Okay, now NBS and lights from exam 1, okay? And this is also free radical halogenation, similar to Br2 in light. But what's different is the position where you're going to add that bromine, okay? And it's going to be specific for the allelic position, okay? And all that means is if you have a double bond in a molecule, right, it's the carbon that is adjacent to that double bond. In this one, it would be that one, okay? Can we add the bromine to this one? Why not? There's 4 bonds to carbon, right? 4 carbon bonds. There's no hydrogen. There's no hydrogen to substitute. So very good. It's not going to go there. So you only have one site that it can go, right? And let's put that in the box. That's the first one. You have this double bond, and we replace that hydrogen on that red dot. We replaced it with a bromine. Okay, but now we still have another product, right? So in order to do this, what you want to do is draw the resonance structures, okay? So let's look at this over here. I'll erase that so we don't get confused. And what you're going to get as an intermediate, remember, this is free radicals. So what you're going to get is at that site where we showed in the other product, the bromine, right, getting attached, you're going to have a free radical intermediate, okay? And instead, like in the product right there, what happened was you had this, right? They met, that's how the bond to the bromine formed. But we want to show the resonance. You can do resonance with free radicals too, right? Not just the lone pairs and the negative charge. So what we're going to have is half arrow. This comes down. Over here, this comes down. You're forming a double bond. And then from the other side, so you have the two pi electrons, right? The other one, right, is going to go onto that carbon, okay? And that's the carbon. Now you're going to have a free radical on that carbon, and you're going to do the same thing. The bromine free radical and that free radical meet in the middle halfway, and you're going to put the bromine onto that carbon, okay? Alrighty, so we have our double bond. It formed over here now, and our bromine is right over there. Okay? Sounds good? Yay, we're done with reactions. Any questions in general about those? Okay, facts. If you guys have any questions about those, I'll stay after for a bit to answer that. I'm just trying to finish so we can get through it because we're almost hitting 9 o'clock, okay? Okay, so let's start with number 6. Or where's number 1? There's number 1. So does the following equilibrium lie to the left or to the right? Okay, so this right here is an acid-base equilibrium, right? Acid is reacting with a base. And then on the other side, you're also going to have an acid and a base, okay? So you want to identify those on each side of the arrow, okay? So on the left side, which one is going to be acting as an acid? I'll zoom in a little bit. Yeah, definitely. Hydronium, right? Has a positive charge on there. So it's more likely to want to donate that proton to somebody. And then on the other one, this right here has a lone pair. It's more likely to act as a base between these two. So this is your base and acid, okay? Now we're going to go to the other side, right? The other side, so basically, you're going to have this acid-base conjugate pair, okay? And so on the left side, the CH3NH2 was the base, right? It's going to get protonated. And so on the right side, now it's going to be the acid. So right here, now it's acting as the acid. And that means the other piece that's there, the water, should be acting as the base. Okay? And you got to have both on each side, okay? Now we're trying to figure out where the equilibrium lies. So the equilibrium is going to lie to the side that is more stable, right? Equilibrium lies towards stability, all right? So another way of asking us this, right, is which side has the molecules that are more stable, okay? So I'll just write, which are more stable, right? Another way of saying that is which ones are weaker acids and bases, right? But I like to think of it in terms of stability, right? We're going to lie towards the stability. So you want to compare, which ones are we going to want to compare, right? So let me put this with this acid, this is its conjugate base, okay? That's the acid-base conjugate pairs, all right? So which ones we want to compare are always going to be the ones, I think it's easiest to just compare the ones that have charge, right? When you have a charge on something, it's destabilizing it. So why not we compare that and use the factors that we know and pick which one's more stable. So which ones have charge? It's going to be the hydronium, and it's also going to be this one right here, okay? So we're going to compare between these two and figure out which one is more stable, right? Or which one's weaker of an acid. So we have a positive charge. On the left one, the positive charge is located on the oxygen, right? So we have a positive on oxygen. On the right acid, we have a positive on nitrogen, okay? Which one is more stable? Nitrogen. Why would you pick nitrogen? less electronegative. Exactly. They're on the same period in the periodic table, but the nitrogen, less electronegative, so more stable. With positive charge. It's better able to bear the positive charge on it, okay? So if this one, right, if this one is more stable, that means it's the weaker acid, right? Something that's more stable is less likely to go and react and act like an acid, right? So you could write weak acid or more stable, right? And honestly, right then, I would just stop and be like, okay, we found the right side more stable. We're going to just say lies to the right. Boom. You don't have to go and check the rest of it, but you can if you want to, right? You can, I think it's best to compare the two that have the charge, okay? This right here and this right here, you can compare them in the sense of oxygen is more electronegative, so it wants to keep its lone pair to itself. In comparison to the NH2, right? Did I say more or less electronegative? Oxygen is more electronegative. I don't know if I said less or more. But oxygen is more electronegative. It wants to keep that lone pair to itself. Less likely to act as a base. Okay? So this right here is the weaker base as well. Weaker in comparison. Okay? So it's going to lie towards the right. Okay? And then for these right here, identical, structural, enantiomer, diastereomer, we want to pick between these. First of all, let's check out the structural isomer, because no point in doing the rest if we can already identify that these are structural isomers. So that just means that the connectivity between the different atoms is different, okay? Same atoms, but the connectivity is different. Okay, so if I look at these, they're all connected to the same thing, right? You have both of these are carbons with these same 4 groups attached, just where they're attached is what's different. Okay, but it's still a carbon attached to a bromine, carbon attached to this double bond group, carbon attached to ethyl, and so on, right? Carbon attached to this, and then this also has those same 4 groups attached, okay? So we're going to knock out structural isomers. Right? Because what's different about these is the way that they're oriented in the space, not their connectivity, okay? And we have how many chiral centers being shown? 1, right? Each one has 1 chiral center. So which one of these other answer choices we can knock it out right away? Diastereomers, because diastereomers, you need more than 1 chiral center, and we don't have that. So let's knock it out. So we got it down to 2. Right? We got it down to 2, and we got to pick identical or enantiomer, right? And how we're going to do that, I think the easiest way to do it, right, to avoid making mistakes, is we'll just calculate RNS for each of them. And if they're the same, what's our answer going to be? Identical. And if they're different, our answer will be enantiomer, okay? So we'll start with the left one, right? We're talking about this chiral center in the middle. And what is our highest priority group? The left one. Like, I'll highlight. We're talking this chiral center. We're trying to do RNS for it. The bromine. Good job. So bromine is our number 1, right? And then for these, I don't want you guys to make any mistakes. So I would personally just go and say this is a carbon right here. So what I have a carbon, right? And because all of these are carbons, okay? So I have a carbon, and that carbon is attached to a carbon. It's a double bond, right? So another carbon as well. Right, you count it twice. And then it's also attached to that hydrogen, okay? Now, let's move down to the one on the right. We got a carbon as well, and that carbon attached to a carbon, and it's also attached to 2 hydrogens. Okay, now let's look at the third one. So we have a carbon attached to carbon and 2 hydrogens. All right, so which one is going to be number 2? Top one, exactly. Put this as number 2. Because it is connected to 2 carbons, and the others are not, okay? And then these guys are the same, so we have to keep going down the molecule to figure out which one's going to be higher priority, okay? So if you go down to the next carbon, this one right here, and this one right here, right? The one on the bottom is a carbon that is attached to bromine, right? Versus the one on the top is a carbon that is attached first to hydrogen and hydrogen and hydrogen. So right away, we need to pick the bottom group to be our number 3, okay? You guys see that? Carbon attached to bromine. And this is going to be our number 4, okay? Now we're going to draw our circle, go from 1 to 2 to 3, ignore wherever 4 is, 1 to 2 to 3, right? And when we do so, that tells us R. But we got to pay close attention. Is our lowest priority group going away from us? No, right? Our lowest priority, the number 4, is right here. Right? This is a Fisher projection. So it's just like a bow tie, someone wearing a bow tie. The horizontal comes at you in the space, right? So our lowest priority group is not coming, it's coming at us. It's not going away. So for that reason, what do we have to do? We got to flip it. We got to change it. And so we're going to say this is actually S, okay? Cross out the R and it's S, okay? Now we got to go to the other side and see what we have. The other molecule, rather. Right here. So we already indicated on the left side what were our highest priorities. So we found that it was the bromine as our number 1, the one with the alkene as our number 2, the one with the Br at the very end was our number 3, and just the ethyl was our number 4, right? Let's do our arrow, 1 to 2 to 3, right? And our lowest priority group, is it going away from us? Number 4? Yeah. It's going away from us, so that's okay. So we got S, right? We got S and S, so what should our answer be? Very good. Should be identical, okay? All that happened here is like similar to a tripod, right? Or rather a wheel, it just, everything flipped. I can draw that for you guys if you want to see it. This went here, this bromine went to the other side, and this came down. Right? So you just spun it. You didn't break any bonds. You just spun it. So it's identical. Okay? For enantiomers, you would have had only 2 groups change. Right? Single swap rule. You change 2 groups, makes it an enantiomer. Okay? Now let's do number 3. Okay, consider the substituted cyclohexane below. In the more stable chair conformation, more stable, that's important. How many methyl groups are in the equatorial position? All right. So for these, there are some like tricks and faster ways to do it. I really just want to show you guys both chair conformations. I think that's the way to ensure that we won't get anything wrong. So remember, we have our chair conformations. Draw it like this, right? And there's going to be a ring flip. Right, isomerizing. It's changing between the 2 versions. All right, so you just pull one side up and we got a ring flip. These are our 2 conformations. Now, right, if the question gave us, let's say in the molecule that was given, let's say that it gave you like an isopropyl group or a terbutyl group, then right away you can pick which one is the more stable chair conformation. You just want to put that isopropyl no matter what. You just want to put it on the equatorial position. But here, there isn't a group that's particularly bulkier than the others, right? An ethyl versus a methyl, you know, there's 2 ethyls and how many methyls, right? 1, 2, 3 methyls. So for that reason, I think we should draw both. If it was an isopropyl, I would skip the step and go straight to the more stable one, okay, by picking that the isopropyl should be equatorial. Okay, here what I want to do, arbitrarily pick any of these carbons in the ring and pick it to be your number 1. Bye. So let's just pick the top one. 1, 2, 3, 4, 5, 6. So you go all the way around, okay? And then let's go to our chair conformation. Do 1, 2, 3, 4, 5, 6. And it doesn't matter, right? You guys, this is just us numbering it so that we can make sure that everything matches up, okay? So we're going to go to our number 1 carbon. Our number 1 carbon right over here. And we need to pay attention to what is on dash and what is on wedge. So if something is on wedge, right, it's not telling us anything about axial equatorial. It's telling us up or down in the space. So if the CH3 is on a wedge, is it up or down? Up, right? So this guy in both our chairs needs to be up, okay? And then the ethyl group, it's on a dash, so it needs to be down, right? So we'll go to our number 1 carbon that we just drew in that first chair conformation. Axial always goes towards the vertex. The vertex is pointing towards the axial. Okay, so equatorial, the horizontal line is going up for our number 1. So we want to put our CH3, we want to put it on the one that's going up, right? So I'm going to pick the equatorial one, just like that, okay? The one that's going down is the ethyl, so I'm going to put CH2, CH3, okay? Then let's move forward. We'll go to the number 2 carbon. Same idea, axial vertex pointing up, equatorial going horizontally down, right? And what we have on that carbon, the one that's going up, it's a CH3, okay? So the CH3 is axial on that carbon, on the number 2. And then the hydrogen, of course, is going equatorial. Now move forward to the 3. It's just hydrogen, so ignore it. Move forward. Number 4, axial up, equatorial horizontally down, right? And right here, we have the CH3. CH3 going up or down? It's down, right? So at our wait, did I do something weird? Yeah, no, that's good. So our CH3 is the one that's going down, right? And then the one that's going up, axial, is the hydrogen, okay? Now, our number 5, this is going down. Same idea, down, up horizontally, right? And so the ethyl group is going down, so that's CH2, CH3, and then your hydrogen is the one that's going up equatorial, okay? And then at our number 6 carbon, both hydrogen, so we ignore, right? We got our first chair conformation. Now we got to draw the other one, and you can do it the same exact way, right? You look at that original molecule and go and identify what's up and what's down, okay? Or you can just look at the chair conformation we drew and flip every single thing. Whatever was axial will now be equatorial. Whatever was equatorial will now be axial, okay? Let's number the chair, right? So we did a ring flip. So whatever was pointing down, like I'll highlight it, this right here, that's pointing down, now it's the one that's going up. So the number 1 carbon is now up here. Okay? Does that make sense? And then the number 6, you follow it down. You follow it counterclockwise. So it's going to be 6, right? And then 5. And then, wait. Yeah, 6, and then 5. And then we got 4. And then we have 3. And then we have 2. Okay? Does that make sense? How we did that? The ones in the middle, these guys, stay the same. Notice that? 2, 3, 6, 5, stay the same. The only thing is the edges are flipping. Okay, so now we want to quickly go through and we want to write every single one. So let's go to our number 1. Got something going up, something going down. CH3 goes up, right? We have the ethyl group going down. Or, yeah, ethyl group, how am I going to fit it? Okay, it's kind of small, but that's an ethyl group going down, okay? And then we go to our number 2 carbon. Number 2 carbon, what's going up is the CH3, so it's going up equatorial. Okay, number 3 carbon, only hydrogens. Number 4 carbon, CH3 going down, right? That's at our number 4, right? So the CH3 is going down just like this, and then it also has a hydrogen attached there, okay? And then our number 5 carbon, right, axial, equatorial, right? What's going down is the ethyl, just like that. And the hydrogen is the one that's going up, just like that, right? And then what do we have left is this, the carbon number 6, and carbon number 6 just has hydrogens, okay? So we put the 2 chair conformations. Now the question is asking us for the more stable one. So we have to decide which one out of these 2 is the one that is more stable, okay? And that's dependent upon the groups, how many we have equatorial and how many we have axial. So we can write Like this is chair A. Okay, so chair A. What's equatorial and what is axial? Okay, so how many groups, what groups do we have equatorial? I'll highlight them. So we have, let's pay attention to our bulky groups. All right, well, both those ethyls, right, or axial. So, wait a second. Did I do anything incorrectly? Did anyone notice something incorrect? Because we should have. Oh, no, it looks good. Sorry about that. I got confused for a bit there. So, sorry about that. So your letter A, right, it's going to have, what's equatorial? The orange CH3, and then also that CH3, right? So you got CH3 and CH3 equatorial. Okay, and then what do we have axial? Exactly. So we got 2 ethyls, yeah. And then we also have a methyl, right? Right, so those are the ones that we got axial. So, we have 2 ethyl groups that are axial. Let's compare to the other chair conformation, the B chair conformation. Okay, and pay attention to what we have equatorial. So I labeled the equatorial stuff, what color? Orange. So orange, we got the CH, no. We got this ethyl group as equatorial. We have this ethyl group equatorial. And then we have this methyl group equatorial, right? And then let's pay attention to what we have that is axial. So I labeled the axial stuff in purple. So I'm going to put CH3, right? And then we're also going to have that CH3 that's axial. Do we have anything else that's axial? Nope. 1, 2, 3, 4. Right? We got it all, right? We're good? Are we okay? Yes. Okay. So which one is going to be more stable between the two, A or B? B. Very good. So B is going to be our more stable one. So I'm going to say B, more stable. All right. So let's go back. It didn't just want us to find which one's more stable. It wanted us to find how many methyl groups are in the one that's more stable and how many are there. Just 1, right? So our answer is going to be 1. It's just this guy right here. Let me show you guys. It's just this one. All right? Answer is going to be 1. Sounds good? Okay. Any questions about that? No? Y'all are good? Okay. So now let's do the resonance contributors and place the contributors in order of increasing importance to the hybrid. So another way of asking this is just which one of these contributors is the more stable one. That's the one that will contribute more to the hybrid, okay? We're looking for the one that's the most stable. The first one, we have a positive charge on carbon, right? Right away, that needs to signal to you that it's not fulfilling the octet rule, okay? So that's very unstable. So I'm gonna write here, no octet, right? And then you also have a hydrogen here. So there's six electrons, not 8. So it's not fulfilling the octet. And then let's pay attention to the next one. So the positive charge, right, is on the oxygen. So it is fulfilling the octet, right? So that's good. So that's more stable. And you have a positive charge on an oxygen. So that's a bummer, but it's still fulfilling the octet rule. So it's going to be more stable than the one on the left, okay? Now let's look at the one on the furthest right. So are we fulfilling the octet rule? Yep. So you have 8 electrons involved there, right? So it's fulfilling the octet. So that means it's more stable than the one on the furthest left. So right away, Octet rule is priority, comes before everything. So I'm going to put that as my number 1. It's the least stable contributor, okay? Contributes the least to the hybrid. Now between the middle one and the one on the far right, which one is more stable? The third one, exactly. And why did you pick that? Nitrogen is less electronegative, right, than oxygen, right? So having a positive charge on a nitrogen is more stable than having a positive charge on a more electronegative atom, which is oxygen, okay? So that's going to be our number 3, and this is going to be our number 2, okay? Octet rule comes before all. Okay, and then place the hybridization of the oxygen atom in the box, okay? So when you have resonance, you're not going to change the hybridization of an atom, right? It's always going to be in the lowest possible hybridization. That is the most stable hybridization that it can be. The more S character, the more stable, the better, right? So we're going to compare between all of these. So the oxygen in the first resonance contributor, what is its hybridization? Right here. sp3, very good, right? 4 electron groups. In the middle, what is our hybridization? sp2, yep. And then on the furthest right, what is it? sp3, you have 1, 2, 3, 4 electron groups. I'm talking about this one right here, this oxygen, right? 4 electron groups, sp3. So what should our answer be? The sp2, because it is the lowest hybridization out of these. So the oxygen is going to take that hybridization. Does that make sense? Okay. Now let's do number 5. So consider the reaction rates of the compounds below with NaI in acetone and place in order of increasing reaction rate, 1 being the slowest and 3 being the fastest. All right, so you need to know what NaI in acetone is doing. Okay, so what type of reaction is going to take place here? Boom. Strong nucleophile aprotic solvent SN2. How many steps does it take for SN2? 1. Concerted mechanism. So you're going to be looking at the transition state and how stable that transition state is, okay? You can think of it as a carbocation in a sense, right? So let's say right here, the transition state is going to look, the leaving groups are going to be in the midst of leaving, right? They're going to be in the midst of leaving, and you're going to be now forming a positive charge on that carbon, right? Where the nucleophile I minus is now going to substitute and attach itself, right? So you're comparing positive right here, right? And positive right here, and positive right here, okay? So before we even look to that, you guys, right? Well, doesn't really matter before, but what you want to look at firstly is going to be the degree, right? Where I put the positives for all of those, where the leaving groups are, you want to look at their degree. So, and what I mean is primary, secondary, tertiary, right? So the first one, right, what is it? Secondary, right? And then the one in the middle, what is it? Secondary, And then the one on the far end, what is it? Secondary. So all of these are secondary, right? So we cannot differentiate based upon the fact that it's secondary, okay? Unfortunately, if you had one that was primary, right away, we're going to go with that one to be the fastest, alrighty? So what we're going to do is compare where these, in our transition state, when we're putting this partial positive charge there, right? Let's compare a positive charge going onto this carbon. Let me get a highlighter. Right there, right? So once the bromine leaves, what is the hybridization of this atom? Once the bromine leaves, after it left. With the bromine sp2, but after sp. Yes, so after Br leaves. Was that a hiccup? It's going to be sp, okay? And then the other guys, right? What are their hybridization? Like the first, let's look at the first molecule. What is its hybridization? We still have a hydrogen there, right? Are we clear? We still have a hydrogen. So what is that hybridization of that positive? sp2? Okay, sp2. Okay. And then the one at the furthest end, what is it? This one right over here. What's the hybridization after it leaves? Also going to be sp2, okay? So you need to ask yourself, a positive charge forming, or a partial positive charge in the transition state, forming on an sp carbon versus on an sp2 carbon, which one is less stable? sp. It is less stable to have a positive charge on an sp hybridized orbital, right? And that is this middle compound that has it, right? That positive charge is going right where that double bond, right on a double bond. That is not going to want to happen, right? So that transition state is very unstable, right? So which one are we going to put as the slowest? The middle one. It's going to be that one, okay? Now between the other two, right? They're both sp. We're putting partial positive on sp2s, right? So what is different between these guys? So that is true that one has resonance, but in SN2, you got to pay close attention to the fact that what also matters in SN2, what else also matters? What's another factor? Steric hindrance. Steric hindrance matters a lot because this is all happening in one step. So in terms of steric hindrance, you have this little nucleophile trying to come and attack, right, at that site where the bromines are located, right? Which one has more steric hindrance? Which one has more things in the way for that nucleophile to come and attack? The left one. So that one is going to happen at a slower rate than the other one, okay? So I'll put this one as number 2 and this one as number 3. And the reason for that was because of on the molecule, think of all that crowding that the nucleophile I- has to come. It's going to come just like this, right? Also over here, it's going to come and attack right over there, right? The one on the left has this big bulky group in addition, right? They're both secondary, but that has that bulkiness that's getting in the way for that nucleophile to make its way, okay? So that's the reason why that one is less reactive, okay? Does that make sense? Any questions? I can clarify it.
But the one on the left, isn't it have resonance? Wouldn't that make it a more stable intermediate?
Yeah, so that is also a thing at play. But the thing is, so he asked if the one on the left, it also has resonance, so wouldn't that also make it better? Or a more stable intermediate. But the thing is that you're in SN2, right? It's a concerted mechanism. So it's all happening at the same time. So you are paying attention to the transition state. And so that's why I mentioned like that pseudo carbocation, pretending we have that positive charge there. But really a big factor, right? An even bigger factor actually is the steric hindrance, right? Because it's trying to come, the nucleophile is trying to come and attack. So I should have actually explained the steric hindrance first and then look to that partial positive that's forming in the transition state, where you're going to get it on the middle one, you're getting it on that sp. It's going to be sp with a positive charge, okay? Does that make sense?
So does no SN2 on sp2 only apply before the leading charge?
Ooh, so that's exactly the reason. That's another thing. I could have just said no SN2 on sp2 and avoided that whole thing. No SN2 on sp2. And that's the reason why. So I explained it's because having that transition state with the partial positive, right, on that sp hybridized carbon is so unstable to the point that it will not happen. You will not reach that transition state. And that's why they always say no SN2 on sp2, right? That saying, no SN2 on sp2. That's the reason why.
So essentially,
Does that make sense?
before the leading proteins, right?
Exactly. Yeah, it's not even going to happen. So here, for all of these, there's no carbocation that's actually forming. I show the carbocation, and Dr. Bean will do that as well, just as a way to explain in a sense, but there's no carbocation at all. It's really a partial positive of the transition state. That's a really good distinction. Okay, good question. Okay, but no SN2 on sp2, so that right away has to be your number one. Okay, so place the compounds in order of increasing rate of dehydration, and 1 being the slower, 2 being the faster. So you need to know dehydration is the removal of water, and you're going to result in a functional group that is the alkene, right? So this could be like H2SO4 in heat. When you have H2SO4 in heat, right? Acid catalyzed dehydration, you're going to protonate the OHs, right? You're going to protonate the OHs, form water as a good leaving group for both of them, okay? Then water's going to leave, and so here we have the formation of the carbocation. This would have left, giving us carbocation. This would have left, giving us carbocation, okay? And now we have to ask ourselves, which one of these two is more stable? The one that is the more stable intermediate it would have been more reactive. It's more likely to do dehydration, right? Its rate is higher because its intermediate is more stable, more likely to go in that direction, okay? We're forming the carbocation. So which one is going to be more stable? The first one. Why'd you pick the first one? Exactly. So the first one can have resonance. He's talking about that resonance structure. You can displace the positive onto the oxygen. That's more stable intermediate. It's more likely to happen. This is going to be our number 2. And then our slower one is going to be our number 1. Okay, resonance is a stronger factor at play here than the inductive effect of that oxygen. So if the compound below can be used to form a Grignard reagent, place Y in the box. And if it cannot, place N in the box. So our Grignard reagent, is it a strong electrophile or nucleophile? Grignard. Nucleophile, right? So if it's a strong nucleophile, that means it is going to react with anything that is a good enough electrophile, right? So you do not want a partially positive or an electrophilic site on the Grignard, the compound that you're using to make your Grignard. It will just ruin the Grignard, right? Because your nucleophile will go and it will attack itself at that electrophilic site, okay? So the one on the left, right? When you're creating the Grignards, you always want to have a halogen, right? You cannot have fluorine. All the others except for fluorine. So you have that here, right? But you also have this acidic proton, right? That terminal alkyne, that proton is acidic enough for if you were to try to make a Grignard, the Grignard is going to react with that acidic proton right here, okay? So when it asks us if we can use this to form a Grignard, the answer should be what? No. Very good. It's going to react. Now, let's look at the other one, right? So we have the halogen, not fluorine, we're good. And in addition to that, do we have a site on this molecule that is electrophilic enough for a Grignard to attack? No, exactly. So our answer for this is perfectly good. We can use it to form a Grignard. So what do you use to form a Grignard? Like, what do you put on the arrow? Ether, right? Magnesium and ether. So isn't this right here just an ether? Like a 5-membered ring ether? We use ether to make a Grignard, right? So the reason why they use that is because it won't react with the Grignard. Unless if it's an epoxide. Epoxides will react, okay? 3-membered ring will react. Okay, so the answer for that is yes, right? It will form the Grignard reagent. Okay, now let's do this one right here. Examine the spectrum and the compounds below. Place the letter of the correct compounds in the box beside the spectrum. And so right here, you're given 4 choices. So we're going to do process of elimination to figure it out. This is our IR, right? In this region, we have a fingerprint. So we're going to cross it out. And what stands out to me, right, below, to the left of the 3000, what stands out to me is these guys right here, right? So what do those indicate? NH2. There's 2 peaks. There's 2 absorptions like that, right? That's what's telling us that it's 2 NH bonds at play. If it was only 1 tooth, tooth like that, then it would be just an NH, one single NH, okay? But it's an NH2, right? So just based upon that fact and identifying that one, we can already pick C, right? The option B would want to see a broad OH in this region right here. The lack of that tells us that it's not the OH, right? The fact that there's 2 teeth right here, remember, 2 teeth tells us that it's going to be NH2, 2 nitrogen hydrogen bonds. So that just shows us 1, so we can cross that out. And then the C triple bond N would show up in the triple bond region, which is like about right here, right? And there's a lack of that, you know, and there's a dipole moment. It would be like a very broad thing right here, so, or a very deep absorption right there. We don't have it, so that's telling us that D is not the answer, and the answer is C, okay? So sometimes you want to use the lack of something in order to figure out the answer. Okay, so for number 9, this is proton NMR, and it wants for us to say, so it says, what are the theoretically predicted multiplicities or splitting patterns of the signals for the protons labeled A and B? All right, so we'll just start off with A and B and see what we have, okay? So our number A, or letter A, sorry, number A. Our letter A is that one right there, okay? And what's going to happen? So splitting, remember, your neighbors are what's going to split you. Not, and here this is a bad example because it's a part of an alkene, so it's an exception to that rule. But basically a better way to say it is that differing or non-equivalent hydrogens nearby, those are the ones that are going to split you, okay? So something that is non-equivalent, right? Non-equivalent hydrogens will split each other, okay? If they're equivalent, they're not going to split each other. They're the same, okay? So we are going to look at that carbon that has the hydrogen A, okay? We're going to look at this right here, right? And on that carbon, we have a differing environment proton. This proton right here is different from that proton, right? The reason why, you're saying, oh, but they're both connected to they're both a part of the alkene, right? But it's because an alkene, those pi bonds, they cannot freely rotate. So they're stuck in place in that form, okay? So this bottom hydrogen is next to things that are different. It's next to this big group, the CH2 with the benzene, versus the one on top is not, okay? So that's why they're different, even though they're located on the same carbon. And you'll see that with the double bonds, okay? So if that's the case, we just do the N+1 rule, remember. So N+1 rule, you're going to take whatever the N is, so that's 1, that's referring to this proton right here, plus 1. Okay. Now we're going to look at the neighboring carbon and what we have, okay? The neighboring carbon is this one right here, right? So how many non-equivalent protons do we have there? 1. Exactly. So we're going to put another parentheses and say 1, N+1, so N is 1, and we're going to get that. 1 + 1, 2, so we got doublet of a doublet, DD. You can say DD, right? Or you can just put, if it's doublet of a doublet, right, that's 4, so you can just say 4 lines. Up to you, whatever you prefer, okay? Any questions about that? The neighboring carbon, I'm not sure what you're talking about. Which hydrogen are you talking about? A or A, right? Yes. So A, on that carbon itself, right, on that carbon itself, it has another hydrogen coming from it, which is a different environment from itself. So that's why it's going to split. That's why they couple with each other, even though they're on the same carbon. They're different environment. Okay. And I can explain that to you afterwards if you want. So then HB, multiplicity of HB, we're going to go to HB. That's this guy right here. And from the left side, right, so right here, do we have any hydrogens? No hydrogens. So that's like 0 + 1, right? So ignore it. Now let's look from the other side. So we have a CH2 group attached. We have another CH2 groups. Are these CH2s equivalent to one another? Yeah, right? It's just two ethyl groups. This ethyl group is equivalent. Do you guys know what I mean when I say equivalent? Same environment, okay? Connected to the same things. So what that means is in your N+1 rule, what you got to do is you got to put 4, because you have a CH2, that's CH2. So in total, you have 4 protons of the same, they're equivalent, the same environment protons, and you do 4 plus 1, okay? And of course, the other side, we said that there was none. So for that reason, we're going to get this is equal to 5. So in our box, we'll put 5 ions, okay? Or pentet. Now, let's do number 2. So number 2 says, under ultra-pure conditions, what is the theoretically predicted multiplicity of the signal for the proton labeled C? So you got to pay really close attention to this right here, where it says ultra-pure conditions. That makes a difference. So let's look at proton labeled C. It's this guy right there, right? And so it's going to be split for sure, right? It's for sure going to be split by the one to the left of it because it's not equivalent to itself, right? Like this CH2, these hydrogens are not equivalent to the hydrogens of the CH2 to the left, right? So those are going to split it. So you're going to do N+1 in parentheses, okay? Now, the question says under ultra-pure conditions. And what does that mean? It means that it's so pure to the point that there's no impurities, no acid-base, weak acid-base impurities present. That means no H2O is present, right? So if there's no weak acid base present in there, then that means this right here, these hydrogens on the NH2, right, if they're not present, there's going to be no acid-base equilibria. That proton is going to stay there, right, for long enough for the CH2 protons to come and they're going to split each other, all right? So when you have ultra-pure conditions, the hydrogens, the protons on OH, and the protons on NH, right? Both of those, right, are going to participate in coupling, are going to participate in splitting. So what you do, we're looking at protons of C. So what you do is 2 plus 1 as well, because we're considering the NH2, those two protons on the NH, on the N, okay? So that's just going to be 3. 3 times 3, what is that going to give us? 9. Okay, so we put 9 in our box, okay? You could also put triplet if you wanted to. Okay, now we're going to do the last one, number 3. So theoretically predicted multiplicity of the signal for a carbon atom labeled D in the proton spin coupled C13. All right, so what's important here is the fact that it says proton spin coupled. That's important. And now we're talking about carbons. Same theory as if you're talking about protons, right? We're just talking about the nucleus of carbon. Same idea. We're going to look at that carbon, the one that's it's looking for D, right? So we need to find where that D carbon is. It's this one over here. That one right there, right? And if it says proton spin coupled, it means that the protons that are on that carbon are going to affect the splitting of it, okay? Not the adjacent, this is different. Not the adjacent hydrogens, it's the hydrogens that are on that carbon that you care about. So if you have 2 of them, you do N+1, right? Same idea. You do N+1, and what you get is 2 plus 1, okay? And that's going to give you 3. So that signal is going to show up in 3 lines, or as a triplet, okay? Okay, you can write either one. Is that the end of facts? Yay. Okay, so we finished with facts, and then we're going to do nomenclature. I know a lot of people don't want help with nomenclature. I'm going to do it anyway. But do you have any questions about facts before we do nomenclature? The last one for the carbon 13? CD, let's look at it. So CD, right, it's just the protons that are on that carbon that are going to split the signal. So you have two hydrogens, right, on that carbon. That's why I did 2 plus 1. Okay? Alrighty. Are you good? Alrighty. So we have nomenclature here. We're almost there, you guys. We're almost there. And of course, it says give the IUPAC name. Doesn't say common name. Gives IUPAC name. And you're just going to want to find the longest chain that has your highest priority group. And on number 1, do we have any higher functional groups? Thank you, Bernard. No, we don't, right? It's just a cyclohexane with alkyl groups, right? So we're not going to worry about alcohols, any of that stuff. We just want to find the longest chain that we can, okay? And to me, it looks like the longest chain is the cyclohexane ring, right? You guys would agree? That's a cyclohexane, okay? The other one would be 1, 2, 3, 4, and then 1, 2, 1, 2, 3, 4, 5. Yeah, so those are not longer than 6. So that's why I picked the cyclohexane. So in my parent, I like to write the parent over here. And I'll just put cyclohexane, okay? Now what we have to worry about is our substituents, right? And the reason for that is because we need to decide which way we want to number the ring, right? We have the liberty to pick. We want to put one of the substituents at number 1, but how do we know which one is going to be our number 1? Okay, that's the thing, right? So we need to figure out our substituents before that, and then number it, okay? So let's look at the substituent over here, like the one that's coming from the top, for example. Of course, the first carbon that comes off is going to be our number 1. Then we go number 2, number 3, and number 4, okay? So 4 carbons, what our prefix should be? Gotta be butyl, right? So we got a butyl, and then from that butyl, right, this is like our pseudo parent, right? We have from the number 3 carbon, we have what group? A methyl. So for that reason, I'm gonna put 3 methyl butyl, okay? And of course, we'll put parentheses because this is, complex naming. We'll put the parentheses, and then later on, we're going to indicate where it's coming from the ring once we decide which way we want to number the ring. Okay, so let's look at the other substituent. This is always going to be our number 1, the first carbon, okay? 1, 2, 3, what our prefix should be? Propyl, exactly. And then what do we have coming off of that propyl? An ethyl. So we're going to put ethyl propyl, right? And then from our number 1 carbon, that's where the ethyl is coming off. So I'm going to put the 1 right there in front of the ethyl. Okay, and you do have to indicate the 1 for that. And then after that, remember, we're trying to figure out which way we want to number this ring, right? Are we going to put the 3-methyl-butyl as our number 1, that's our number 1 carbon, or are we going to put the 1-ethyl-propyl as our number 1, okay? And what factor are we going to use here? The alphabet. So E comes before M, right? So that's the one that on our ring, we want to make it our number 1. So I'm going to erase the stuff that I drew because we got our names down. Substituents, and so the 1-ethyl-propyl was this guy right here. So I'll put the 1 right there, and of course we want to go in a way that it's going to give us the lowest number of substituents. So if we went counterclockwise, let's see, 1, 2, 3, 4, 5, 6, you would get it on 4, and if you went clockwise, you would get 1, 2, 3, 4. Both ways are 4, doesn't matter, okay? So that's how we're going to number it. Right? And now we can indicate where those substituents are coming from, right? So the 1-ethyl-propyl, right, is now coming from our number 1, and the 3-methyl-butyl is coming from our number 4, all right? So we got the substituents, and now what is left for us to do? what's the last thing? We got parent, subs, and then our last title needs to be stereo, right? So because we have a ring, right, what we want to care about is the direction of those groups, up or down, okay? So they're coming, both of them are going down. Yes, one is equatorial, one is axial. That does not matter. What matters is what is up and what is down, okay? So they're both going down. Do you guys see that? Down, down, equatorial. They're both down. So for that reason, right, are we going to say cis or trans? Cis. So at the very beginning, am I zoomed in enough? We're going to put cis like that and then put a dash, okay? And then after that, we're going to want to put these in the order of the alphabet. So 1, propyl, right? We're going to a number, so we put a dash. Right? Close parentheses, and then of course we're going to end up with the cyclohexane. Just like that. Okay? Any questions?
Why did we take the B of the butyl group?
The B of the butyl group. Ooh, like in the methyl butyl? Yeah, that's a really good question. So you always look at the first letter, right? You look at the N, the methyl, okay? Always the first letter. Like if my name is Sabrina Bitar, you would look at the S. You wouldn't look at the B of Bitar. Does that make sense? Okay, so let's do the next one. And we want to identify our parent. And we want to find the longest chain that includes our highest priority groups. And what are our highest priority groups? Double bonds, right? So we have 3 of them, right? So we're only going to be able to include 2. There's no way for us to get to include 3, so we're just going to find the longest chain that we can that's going to include those 2. So that looks to me like it's going to be this one. Like that. Let's count it out to be sure. We got 1, 2, 3, 4, 6, 7, 8, 9, 10. So that would be deca. Versus if we did the other branch, you know, that's coming off, we'd get 1, 2, 3, 4, 5, 6, 7, 8, 9. We'd get nana, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is the longest one. We picked the longest one that has the most double bonds in it, okay? And our prefix we said was deca, right? So we'll put dec, just like that. And then you need to figure out how many double bonds you have in our parent, right? And we have 2. Yes, we have 2, right? So you're gonna want to indicate where are those double bonds coming off. The first one, right? And there's actually a specific reason why I numbered it from left to right, right? Because the alkene has to be the lowest number, okay? So that was actually coincidentally correct. But you would want to put the deca 1, comma, right? And then our second double bond is coming from 6. So 1, comma 6, right? Dash line. And how many double bonds we have? So what do we have to say? Exactly. Deca 1, comma 6 diene. That is our parent. Okay. Now let's look at what we have coming off of the parent. So our substituents, right? And we have firstly at our number 5 carbon, we have like this complex substituent. We also have a bromine at our 7. Let's just do the bromine first since it's easier. So 7 bromo, right? And then from our number 5, we have 5 dash, and then we're going to want to do the complex naming. So we're going to start at that first carbon, 1, 2, 3, right? And so what's our prefix for that? Pro, right? So, and you have a double bond. So it has to be propenol, right? So we're gonna put another parentheses, right? Because 5 was indicating where that was coming from our parent, and now we need to indicate where the double bond is inside our substituent, and that is the number 2 carbon. It's kind of hard to see. It's this one right here, number 2 carbon, propenol. So 2 propenol, and then you put it in parentheses just like that, okay? 7 bromo is not complex substituent. That's why I did not include the parentheses, okay? So yeah, so you would put the 2 inside because you're describing the substituent itself where that double bond is located. Oh, I've never actually seen it drawn. I've never seen it drawn like that for the substituent, so I'm not sure. I've only ever seen it drawn where it's in the front. For the parent, of course, you can do one or the other. Yeah. So I wouldn't be able to tell you. You could ask Dr. Bean if you want to. No. Good question. So, okay, so we did our substituents, and now we got to consider our stereo. So what do we have to look at? Do we have anything? E and Z for which double bond? 6 and 7, right? Not the others because they're terminal and they have 2 hydrogens. So what we're going to do, we're going to cut it right down the middle, compare just the left side, just that carbon number 6 and what it has attached to it. So here you have a hydrogen going down and you have this big group going up. So of course the higher priority one is going to be the one that's going up. Okay, we don't even have to go look carbon and so on and so forth. So heavier or higher priority, I put it as an H, it's going up. Okay, and then ignore left side, look at just the right side, compare what's going up right there. We got a bromine, and we have this carbon chain. What's higher priority, bromine or the carbon? Bromine. So we're going to go with the bromine, the heavier one, right, is going up as well. So is this going to be Z or E? Same side. So it's going to be Z. And then you have to indicate, well, here we only have one internal double bond, so we don't have to say, that it's at carbon number 6. We can just literally put Z, okay? So we put that in parentheses. We go here, we go Z, right? And then we want to put everything in alphabetical order. Yeah.
You have to identify that chiral center.
Is there a chiral center in here?
5.
Oh, yeah. So 5 is a chiral center because it has 4 different groups. Does it have 4 different groups? Yeah, it does. But the stereochemistry is not shown for you. So you don't have to. Versus look at number 3. You see how it's shown wedge and dash, right? That's a really good question. She asked if you have to show the R or S for carbon number 5 because it is a chiral center, but it's not showing you if there's wedge or dash, okay? So you don't know. How would we know how to find that priority? So we got Z, and then we're going to go 7, bromo, dash, and then 5, and that's going to open our complex substituent propynyl, and then it's going to be Zeca 1, comma 6. Let's see if I'm going to fit it like that. Okay? Anything? After the parentheses, like the opening parentheses, or the Z or the Z parentheses? Oh, the closing parentheses, the last one. No, because you're going from letter to letter, you don't have to put a dash. Yeah, you'll keep it as parentheses, and then it's smushed. They're smushed together. There's no space, no dash, no nothing. Okay, so then we're going to do number 3, and of course, we want to find the longest chain that has our highest priority group. So what is our highest priority group here? The alcohol. So ignore everything else. Don't let the alkyne confuse you. Don't care about it. You have your eye on the prize, and that's the alcohol, okay? Ignore it else. Ignore everything else. So we're going to look at the alcohol, and we're going to find the longest chain that we can find that includes that alcohol. And so to me, it looks like it's going to be this guy right here. This one. Right? And it continues in here. So I'll label the carbons that. I'll see that. So if we were to count this out, what would we get? So we'd get 1, 2, 3, 4, 5, 6, 7, 8. Right? Oct. Okay. If we were to count the other route, it would be shorter. It would be shorter of two carbons, of 1 carbon actually. C and C, right? So we're going to pick that one as our parent. Okay, and we said that it's 8 carbons, right? So that what's our prefix? We said it's going to be oct. Oct. Okay. And then what are our functional groups that are present in our parent? Yes, ma'am. Oh, did I count incorrectly? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So it may be hard to see. There's 3 carbons, those ones that I highlighted. Do you see those 3? So 1, 2, 3, 4, 5, 6, 7, 8. I'm counting all the way down. I'm not putting the alcohol at number 1. The alcohol is in the middle. Do you see it now? Like it's let me highlight the entire parent for you. Do you see how that's 8 now? Yeah? Okay, so that's 8. So you don't necessarily have to put the alcohol at the lowest position. That's a really good question. You just want to find the longest that you can, and then we'll look at the numbering, okay? So we got oct, and what functional groups we have? We have the triple bond, and then we also have the OH, right? So in our parent, of course, when we're naming it, we're going to put the alkyne first, right? But we're going to want to know how to number this thing. So we want to put the alcohol on the lowest number we possibly can. So if we were to start from the right, we would have 1, 2, 3, 4. Alcohol would be coming from the 4th carbon, right? If we numbered it from left to right, let's see what we get. 1, 2, 3, 4, 5. Okay. Do you guys see that numbering it from right to left gives us the lowest number, the alcohol? Gives the alcohol the lowest number. So ignore, like I said before, ignore the triple bonds, okay? You guys, when we're doing our parent and we're numbering our parent, pay attention, laser vision on that highest priority group, okay? So we're going to number it. 1, 2, 3, 4, 5, 6, 7, 8, just like that, okay? Now we got to indicate where is our triple bond. It's coming from our number 7 carbon, right? So that's going to be oct 7, right? I'm not going to put an E because we're not done yet. We still have to account for our alcohol. And then our alcohol located on which carbon? 4. So we're going to end it with O. There's only one of them, right? So oct 7, ein, hor, O. Okay? And then we got our parent down on the paper. So now we want to do our substituent. So first of all, there's only one substituent coming off of this, and it's going to be that guy right there, right? So we wanna number it like this, of course. 1, 2, okay. And so what is our prefix for that? Ethyl. And then you have a bromine, so it's gonna be bromo. Okay. And our bromine is coming from that 1st carbon, so you're gonna say 1 bromoethyl. And then you gotta indicate, this is complex substituent, you gotta indicate where it's coming from the parent chain. And so what number is that? The number 4. Exactly. So that's our complex substituent, right? And then are we done? What do we have to do, Jonathan? Stereo. Nice. So we have a chiral center, no double bond. So we're just going to do that chiral center right here in the middle. And what's our highest priority? Sorry? The oxygen, yes. I heard suture. I was like, what? And then, so our oxygen is our number 1, right? And then we'll compare the other 2. Which one would be our number 2? The carbon with the bromine. Yes. Right? Because all of those are carbons, right? So you got to look at what's connected to those carbons. And that one at the top has a bromine, right? So that's higher priority. Okay. So now between the other 2, which one is our highest priority? The left one, the one with the alkyne. Exactly. So that's going to be our number 3. That's going to be our number 4. We're going to go 1 to, just like that. Okay? 1 to 2 to 3. Ignore 4. What should that be? S. Okay. But is our lowest priority group going away? Nope. So we're going to cross it out. That's wrong. And we're going to put R. Right? So it's actually R. And so in parentheses, we'll put R. And then, of course, there's only one stereocenter, right? So we'll just put, we don't have to indicate the number. And we're going to put these in alphabetical order. There's only one substituent, right? So we're going to put 4, okay, and then 1, bromo, ethyl. We're almost there. 4, O. And that's it. That's our name. And we forgot the parentheses, or I forgot the parentheses. You guys didn't forget anything. Okay, and that's that, okay? Okay, so we're done with this. I'm gonna cancel the recording. Let's pray that it works, right? And then I'm gonna say and answer any questions you guys have. And like, kudos to you guys for chucking through it and staying here the whole time. Okay, no problem.
If you stay, we should stay.
What?
I said if you stay, we should stay.
Aww.